Hyderabad. I have moved to NTU Singapore. There I have worked on 3D printing of flash slag binders and also the magnesium based cement. Then I got opportunity to work in the laboratory of construction materials at EPFL Switzerland through the Swiss Government Excellence Fellowship. Then I was there about 1.5 year, and recently I have moved to India during this COVID pandemic situation. I'm stuck here for time being. I have joined at SRM University, Amaravati. It's not Chennai. It's near to my hometown. And with this quick introduction, then maybe I'll move to my research topic. Yes, our current today's theme is the construction materials from industrial waste for sustainability. Then here the question is, why should we work, or why should we focus towards the sustainable materials? And let me take my pointer as well as. Yeah, sorry. And here the question is, why should we work towards the sustainable materials? And if you see the world cement consumption scenario in the worldwide, so maybe this, you can see this the bar chart represents the level of consumption of cement in various countries. And among all, the China and India, these are two predominant countries consuming a massive quantity of cement in the industry, and we are expecting about 3 gigatons of world cement consumption by these two countries by end of 2050, which means we are going to consume, and we are consuming a massive quantity of cement, especially these two countries. And during the cement production process, we are releasing about 5 to 10% of anthropogenic carbon dioxide into the atmosphere. And also we are consuming virgin materials such as limestone as well as clay during the production of cement. And to considering all these factors, then we have to work really towards the development of alternative sustainable materials to meet the required demand of cement in the construction sector. And if you look at the crust earth of our various composition, generally the earth composed of various, these are the predominant elements consist, especially the silica, alumina, iron, calcium, sodium, potassium, magnesium, as well as other elements. And these are the predominant elements present in our earth. And whatever materials we are using or we are producing, and these elements more or less should be present in those materials. And let me show one of the example. And this is the typical composition of the earth crust. And if you compare with our cement composition, and the same elements are present in the cement, but in various quantities. For example, in the earth crust, we have a significant quantity of silica as the sand and or a clay. And here we have a significant quantity of calcium, followed by silica, as well as alumina, followed by iron, and also the other elements. And what I'm trying to say is, whatever materials we are producing, and these elements should be present in those materials and in different quantities. And by considering this as a baseline, and here the question is, what are the source material we have available in our locality to meet the cement composition? And here the question is, do we need to rely only on clinker to produce cement? Well, we have to use the clinker somehow, but we have other supplementary cementitious materials. There we can partially or fully replace with the cement or clinker. And what are those materials are available? We have a limestone from the limestone quarries, and we'll have the fly ash from thermal industry, and we'll have the slag from iron industry, and we have the natural pozzolans are available, and we have the significant quantities of clay is available in our locality. On top of this, we have other industrial waste materials such as rice ash as well as microsilica and silica fume, but the local availability is very important for other waste industrial waste material. And if you compare with the various materials available in our locality, but out of among all, I have to focus towards the industrial waste material, because we have to somehow utilize the industrial waste material to use it for various construction applications rather than consuming our virgin materials. And what I have worked as sustainability moves forward emphasize, I would like to focus towards development of a new cement formulations by utilizing the various industrial waste material. And to reach my goal, then I have chosen fly ash as a waste material to produce alternative binders. Then why I have chosen fly ash as my source material to produce alternative binders? If you look at the fly ash generation and percentage of utilization scenario in India for the past few years, as you can see, the ash generation is increasing year by year, but we can able to utilize about 55 to 65% of fly ash for various applications, and the rest is lying on the earth. And currently, out of 197 million tons of fly ash is generating, out of which 67% of fly ash is being used for various applications. And if you divide the 67%, that's out of 67%, the 25 to 30% of fly ash is utilizing in cement and concrete sector, then the rest is for other applications. Then why we are unable to increase the fly ash utilization in the cement and concrete sector, as it is limited due to the heterogeneity as well as the variable in composition, as fly ash is vary from source to source and within the source. And our intention or our goal is, if you are able to increase the fly ash utilization, especially in the cement and concrete sector, as India is the developing country and we can see the construction activity is picking up on India, and we need a massive quantity of concrete in next few years. And due to that reason, then we have to somehow develop other alternative source materials, alternative binders to meet the required demand of cement as well as concrete in the construction sector. And how can we improve the fly ash utilization in the cement and concrete sector? Then to improve the fly ash utilization, I have identified three major challenges. The one is the characterization. We have to do the proper characterization of fly ash, which means we have to identify the reactive contents and non-reactive contents present in the fly ash once we have received from the thermal power plant. And the second point is the measurement of degree of reaction. And during the, if we use the fly ash as a binder over a period of time, how much fly ash is reacting, how much fly ash in the form of non-reactive. Whether how does the dissolution characteristics take place in various environments. Whether the glass present in the fly ash is dissolving or it's sitting in the ideal in the system. And all these things should understand before we're going to use fly ash in construction applications. On top of this, we have to develop a better analytical techniques to identify, to quantify the reaction pathways and the quality assessment and all these things within a shorter span. Whatever methodologies available as per our code and also whatever the existing methodologies, and all these methodologies required much longer time to get the reactive silica as well as reactive alumina and other parameters in the fly ash. And we have to develop a better analytical techniques to assess the fly ash mechanism. And after considering all these factors, then I have developed various methodologies in my research. And as the fly ash is the industrial waste material that everybody knows that, here my point is the fly ash consists about the glassy particles as well as the crystalline particles. And the crystalline particles, this is the example of the quartz. The crystalline particles are nothing but the proper orientation of silica and oxygen atoms in the structure. Whereas the amorphous glass, it's the irregular arrangements of silica and aluminum atoms in the structure. And if you see the one of the tiny portion of the fly ash, how does the microstructure looks like? And this is at 8 micron scale. You can see the fly ash contains the glassy particles. This is the glass particles. It looks like. And coming to the practical issues, we'll have the as the fly ash is classified into two categories. One is siliceous fly ash, that is called glassy fly ash, and another is calcareous fly ash, that is called typically the class C fly ashes. Then if you see the practical issues, the siliceous fly ash, coming to the siliceous fly ash, we have a significant quantities are available in India. The main disadvantage is it's a very slow reaction. We have to wait much longer time to get it slow. And Excuse me, can you please mute yourself? I'm getting a lot of noise here.
Oh my God.
And coming to the calculus flashes, it is available. Availability is quite low compared to the siliceous flash, and it's a more reactive and it's very heterogeneous as well as very variable. But the most of the class C flashes is utilizing various locations and various sectors. And in my research, I have focused mainly on siliceous flash, as already the significant work is already carried out in class C, and we are using class C very efficiently in various applications. And coming to the class F flashes, yes, the main disadvantage is the slow reaction. And how can we overcome this problem? How can we efficiently we can utilize siliceous flash, especially the class F flash in the cement and concrete sector? And to overcome this problem, then I have introduced a systematic approach to produce alkali activated low calcium fly ash based binders using the siliceous fly ash. And this schematic representation of how the compressive strength occurred in alkali activated fly ash. And here I have used sodium silicate or the sodium hydroxide or the alkali activators to activate the fly ash. The whole process involves the various steps. The first and essential step is the characterization of fly ash and identification of its individual reactive contents. As you can see here, the flash, we have a different particles in different sizes as well as different shapes. And firstly, I have tried to understand the fundamental behavior of the fly ash. How does the fly ash will behave once we have received it from the thermal industry? As what are the reactive portion, what is the non-reactive portion, and how much dissolution will take place, and also all these factors I have identified once I have received it from the thermal industry. Then once I have characterized the fly ash thoroughly, then second step I have carried out what are the process variables that influence on the fly ash character for the reaction product. Sorry, that's not about the fly ash characterization, it's a reaction product. Like what is the role of sodium silicate and what is the role of sodium hydroxide and what is the role of reactive as well as solution ratios and what is the role of temperature and what is the role of water to binder ratio. Here the binder is nothing but the binding material where we used to call water to cement ratio. And also the what is the role of molarity and how does these process variables will influence the reaction product, which means which type of product is from the system, how much quantity of product, and what is the type of product, and also the reaction kinetics. How does the kinetics is going to take place, like how much fly ash is dissolving and how much fly ash is reacting and how much reaction product is formed in the system. And ultimately, as a civil engineer, we have to work towards the strength, how much strength we are occurring ultimately. And the overall approach is for a given fly ash, how does this fly ash process variables and also the reaction product, the type influence the strength development in the alkali activated materials. And my main intention is I would like to focus towards the fundamental understanding of the material behavior. How does the material behave in a fundamental level, in atomic level? And thereby we can optimize the mixed proportions without compromising its performance and also the mechanical behavior. As civil engineer, we used to worry about the strength as well as fracture and also the split tensile and all these factors we have to consider ultimately. Then the whole presentation is I have divided into four segments. The first step I'm going to talk about the characterization part, and the second step is the reaction product, and the third step is strength point of view. And the fourth step, I have carried out some of the experiments using the geopolymer concrete. If time permits, I would like to show those results as well as. And coming to the characterization, to know the importance of fly ash characterization, I have collected fly ash samples from various locations. These are the source locations I have mentioned here. And once I received the fly ash from these sources, I have determined the oxide composition of all these fly ash samples. And the obtained values I have mentioned here. As you can see here, all these fly ashes is predominantly contain the silica as well as alumina, and it's about 80%, 80 to 75 to 85% of the silica alumina content present in all most of these fly ashes, and it's rich in silica and alumina, and thereby we can see a very low lime content. The calcium content is varying from 1 to 4% in all these fly ashes, along with other oxide composition. And finally, as per our IS standard, these fly ash are classified as the siliceous fly ashes. But then finally, I have divided into it's a low calcium siliceous fly ash. Even though it's a siliceous fly ashes, but I would like to call it a low calcium siliceous fly ash. And the next second step, I have used some ritual refinement tool to determine the total crystalline, total amorphous content present in all these fly ashes. And this is the XRD signature of the one of the fly ash. It's the fly ash B as one of the source fly ashes. As you can see here, the fly ash XRD spectra, we have a broad amorphous hump over a 2 theta range from 15 to 32. And also we have different crystalline phases are observed over the spectrum. And finally, I have identified what are these crystalline phases. Then I have identified it's a quartz, malite, there's a predominant quantities followed by magnetite, hematite, rutile in the minor quantities. Then I have carried out the ritual refinement by using external standard approach, and then I have determined what is the total crystalline and total amorphous content present in all these fly ashes. And as you can see here, the total crystalline and total amorphous content is significantly varies from one source to another source. And if we compare like one of the source from B to D, the fly ash B source contain the lower in crystallinity, whereas fly ash D contain the higher in the crystalline crystallinity. Whereas if we compare with the fly ash M and as well as fly ash D, the fly ash D as well as fly ash M is shown more or less similar in amorphous content, but if we compare with fly ash B, it shows lower in amorphous content. As it indicates that the fly ash reactive potential, reactive components, it will vary from one source to another source. And the overall is all these fly ashes, a significant portion is present in the non-reactive crystalline form. The crystalline form, it will not react in the system; it will simply sit in the system. But the amorphous portion, that is the portion is responsible for the reactive potential of fly ash. Then I went one step forward. Then I have determined the reactive silica as well as the reactive alumina content present in all these fly ashes. And this is the fly ash I have represent here. These are the source locations, and also the y-axis represents the total as well as reactive silica. And the total silica, as I said, I have determined by using XRF technique, and also the reactive silica as well as reactive alumina I have determined by using combined XRF XRD technique. And these are standard equations I have used to determine the reactive silica as well as reactive alumina. And as you can see, the total silica as well as total alumina content is more or less same in all these fly ashes with the very little difference. There, as you can see, the reactive silica as well as reactive alumina content significantly varies from one source to the another source. And let me focus on one particular fly ash. If you look at fly ash M, out of 48% of total silica, we have about 13% in the form of reactive, whereas out of 31% of total alumina, we have about 8% in the form of reactive. The results clearly says that the proper characterization should be done before we are going to use fly ash for any type of application. So we should not rely on the total silica as well as total alumina, which misleads our prediction over a period of time. And this is the one of the comparison of the reactive silica content as per our existing methodology IS standard and also our XRF XRD technique for all these fly ashes. And as you can see here, both the methods are shown more or less similar in results with a little difference. And all these fly ashes, the IS standard shows slightly higher value, which means that for the highest standard methodology, we are using the acid technology. Some of the particles are very sensitive to the acid, and all these particles may dissolve. And also, some of the sample during this methodology, some of the sample it may pass through the filter paper, and also some of the sample it may written on the filter paper. All these factors we have to consider while we are using the existing methodology like acid-based technique. And the combined XRF XRD technique, it's a very straightforward methodology and it is not required much longer time. In case of IS standard, we have to wait for 24 hours to 48 hours to get the results for each individual fly ash samples. But the XRF XRD technique, it will take hardly 30 minutes to get the results of reactive silica. And why I am showing this particular plot here, as we can use the XRF XRD technique or IS standard methodology, but both the methodologies shows more or less similar in results. But IS standard method shows slightly higher values, so it may be the reason some of the particles are sensitive to the acid, it may dissolve, and also we have to take proper precautions while we are doing the acid-based methodology. And this is the one of the correlation I have drawn from all these fly ashes. And here the y-axis represents the mullite content, which is a crystalline form, and also the x-axis represents the amorphous iron content. As you can see here, in all the fly ashes I have plotted here, for a source to source, if you compare with one source to source, the higher the mullite content in the fly ash shown, lower in the amorphous content. If we, it means that the mullite place, the formation, the processing conditions is clearly influence the amorphous content in our system, especially the mullite phase. If we have a higher formation of mullite phase, it will clearly reduce the amorphous formation in our fly ashes, because we have to take the proper precautions, the electrostatic precipitator while we are doing the processing conditions. And coming to the microstructure, this is the SEM image of some of all these fly ashes. As you can see, these are at the 100 microns scale. As you can see, we have a different particles in different sizes as well as different shapes. We have a unbroken particles, we have a well-defined particles, and also we have a elongated particles, and we have the blackish particles. And all these elongated particles, unbroken particles, blackish particles are classified as the crystalline particles, which does not have any reactivity. All these well-defined particles, maybe you can see it here that 8 micron scale, and all these well-defined particles are classified as the glassy particles, and we can also call it as the cenospheres. And a group of cenospheres in one sphere is called plerospheres. It's a plenty. And these type of particles or plerospheres or cenospheres are responsible for the reactive potential in the fly ash. These are the particles it will react in our system rather than all these elongated particles and also the broken particles. And there are some of the individual particles I have observed in our fly ashes. I have observed a whitish grid on the particle surface, and these type of particles are classified into iron-rich sphere. And I have conducted the index analysis on various particles to determine what is the uh, product type is present in these particles. And I have also the edges are very sharp edges particles I have observed, and these type of particles are classified as a quartz. It is rich in silica. And the blackish particles are classified into carbon particles. It's typically consists about the carbon. And all these spheres, I have carried out index analysis on these spheres. And all these spheres are rich in silica as well as alumina. Finally, I have classified these particles as alumina silicate glass. And once I have identified the various morphologies and also the reactive potential and non-reactive potential and all the total amorphous content, then I went one step forward. Then I have to identify which type of glass is present in our fly ash. As I said, all these particles are rich in alumina and silica. But if you're able to see which type of glass, like it is a calcium aluminum silicate or iron aluminum silicate or only aluminum silicate glass, that we have to identify. Then this is the one of the XRD spectra of fly ash B, and I have separated the total crystalline as well as total amorphous portion by using poly refinement. As you can see, I can clearly separate the crystalline portion as well as the amorphous portion. This is the amorphous portion of my fly ash. This is the responsible for the reactive potential. Then I have synthesized some of the glasses, which one is the low calcium aluminum silicate glass and another is high calcium aluminum silicate glass. And I have measured the XRD spectrum of these, XRD signature of these two classes. And if you compare with these two classes with our fly ash signature, and whatever the amorphous portion, whatever the signature I have shown here, if you compare with these two classes, our Indian fly ashes, especially the siliceous fly ash, contain the low calcium aluminum silicate glass, which has the well-defined center around the 2θ angle about 22. And this amorphous hump is attributed to the plerosphere, cenospheres present in our fly ash. So it was evident by the previous EDX analysis that these particles are rich in aluminum silicate glass, but we have not defined their which is calcium rich or low calcium. But as per our synthesized glasses, it was evident that most of these fly ashes are contain the low calcium aluminum silicate glass. Then once I have identified the glass, then I have carried out the dissolution studies. how does the glass will behaves in various environments. And before that, I try to identify the total glass content present in our fly ash by using existing methodology, that is 1% selective HF acid dissolution, by comparing our XR of XRD technique, which I have used throughout my research. And as you can see here, this is the XRD spectra of before HF treatment. After HF treatment, the whole amorphous portion is completely dissolved without affecting the crystalline phases, which means that the HF acid dissolution will be dissolve only the amorphous portion and not the, sorry, it's only glassy portion, not the crystalline phases. But this treatment is very sensitive to the time. We have to restrict your time while we're doing this methodology. If you are exceeding your time limit, then it will dissolve some of your crystalline phases as well. As I have observed those values also, but I'm not presenting here. And I try to compare with this existing methodology with the XRF XRD technique with different fly ashes. One which about 50% of total glass, another fly ash is about 40%. And both the methodologies fairly matches and with a very little difference. But I will not prefer the HF acid dissolution because it's a very harsh treatment and we have to wait much longer time to achieve the result. And then once I have identified the, yeah, the glass type, then I have studied how does the glass signature will change over a period of time. And if you, and once we have used the fly ash in various alkali environment, or for example, if you use the fly ash in high volume fly ash or some other application, then whether the fly ash is dissolving, fly ash glass is dissolving, the crystal phase are dissolving over a period of time. What happens when this fly ash is attacked with the hydroxyl ions? Then this is the XRD spectra of fly ash B, and this is the XRD signature at 24 hours. This is the XRD signature at 48 hours. As you can see here, from 0 means from initially to the 24 hours, you can see a reduction in the amorphous phase. From 24 to 48 hours, you can see a completely dissolved amorphous portion without affecting the crystalline phase. Then I have identified at two environments. One is at 1 molars, 2 alkaline environment. Another is at 6 molars, alumina, as well as I have focused only on alumina and silica. Yeah, these are the predominant phases present in our fly ashes. At 1 molar, you can see clearly see from 3 to 48 hours, you can see a clear increase in the alumina element concentration in the solution. And whereas 6 hours, you can see a significant improvement in the dissolution of alumina ions from 3 to 48 hours. From here, from 3 to 48 hours in the case of silica. And by end of 48 hours, most of the fly ash is amorphous glassy phase is dissolved, which means that the alumina and silica species came into the solution. Then what I'm trying to say is the dissolution of fly ash is leads to release fly ash glass is leads to releasing of reactive species such as the silica and alumina into the solution along with the other elements. And this with respect to the time, what happens if we increase the temperature? And the minute when we increase the temperature from 25 to 60 degrees Celsius, from this is the fly ash B, this is the reference sample. Then if you increase the temperature from 25 to 60 degrees Celsius, it's clearly enhance the dissolution mechanism. And most of the fly ash is dissolved by 48 hours. But in case of 25 degrees Celsius, we have to wait much longer duration. As you can see here that 25 degrees Celsius, you can see a steady releasing of reactive species into the solution, whereas at 60 degrees Celsius, most of the fly ash is dissolved by 48 hours in case of 60 degrees Celsius. And the duration is enhanced the dissolution process, and temperature is clearly enhanced the rapid dissolution into the rapid dissolution of glass and releasing a reactive species into the solution. And coming to the second part of my presentation, it's about the characterization of a product. So far, we have discussed about the identification and also the dissolution characteristics of all these fly ashes. Then I'm moving towards characterization of reaction product. What happens once the alkali activation takes place? We have mixed fly ash with some alkali activator, and we have queued the sample. Finally, we are going to get some product. Which type of product it is, and how much quantity of product is formed in the system. And we have to correlate with the compressor strength. How does the compressor strength will correlate with the reaction product as well as the dissolution mechanism? And this the I'll quickly go through this methodology. This is the XRD signature of fly ash B. As you can see, we have a different crystalline phases along with the broad amorphous hump. And this amorphous hump is the glassy phase of the fly ash. And this is the XRD signature of the alkali activated fly ash. You can see the different crystalline phases. I can also see a new crystalline phases. One is here and another is here when compared to this pure fly ash. And along with the broad amorphous hump from 15 to 40 degrees. Here only we have 15 to 32 degrees. And maybe I can show it somewhere here. We can see a clear amorphous portion from 15 to 32, whereas in alkali activated materials we have a two different new crystalline phases along with a broad amorphous sum. One is at it moves from lower angle to theta, another higher angle to theta. And once I have done with the acid dissolution, this is the existing methodology which was developed by the Palamo et al. At 2007. And sorry, able to hear? Maybe I'm getting some noise here.
No, you are very clear. Somebody joined in between, so that.
Okay, fine. Thank you. Yeah, this is after acid dissolution. This is the existing methodology I have used to see whether the existing methodology will dissolve the only reaction product or also the glassy phases present in our fly ashes. And the existing methodology, it dissolves the only the amorphous reaction product as well as the new crystalline phases without affecting the glassy phase of the fly ash. That was evident by the XRD signature. Then the drawback of this methodology. Is it's require much longer time, and also we have to take proper precautions while we're analyzing the reaction product as well as how much glass left over in the system with respect to the time. And we have to wait at least 3 to 6 hours to get the results of how much glass is reacted, how much reaction product is formed during this activation process. And to overcome this methodology, then I have developed a new XRD based direct decomposition method. And this is, I'll quickly go through this methodology. This is XRD spectra of alkali activated fly ash, which I can see a different crystalline phases. The same XRD signature which I have shown here, the same one I have used here. And we have different crystalline phases along with the broad amorphous hump. Then by using poly refinement, I have separated the total crystalline portion as well as total amorphous portion. And as I have explained earlier, the total amorphous portion is considered about shift from a lower theta angle to the higher theta angle after the activation process. Then by using the nonlinear fit algorithm, I have focused this region especially from 15 to 42 degrees to theta angle. And this is the amorphous hump. And by using nonlinear fit algorithm, I have deconvoluted this portion to see how many phases are present in this region. Here I can able to fit two phases. One is at lower theta angle, another is at higher theta angle. The lower theta angle represents the glassy content present in the alkali activated fly ash, which the glass is not reacted. And the upper theta angle, the higher theta angle represents the reaction product formed during the activation process at the particular time. And this methodology is a standardless method, does not require any calibration coefficient and all other factors, and it's required only the signature of the alkali activated fly ash or XRD signature of the fly ash and also the alkali activated fly ash. And this method provides a fast way of determining the glassy content and reaction product content in activation system, and also it will helps to predict the reaction kinetics in the alkali activated system. Then as usual, I have tried to compare with the existing methodology with our XRD direct decomposition method. And both the methods, this is the unreacted glassy content and also this is the reaction product content at three different ages at 7, 14, 28 days. And all these methodologies, at all these particular ages, both the methodologies are fairly matching. Then we can observe the acid dissolution methodology has a higher error bar compared to the XRD direct decomposition method. And this higher error bar is due to the some of the, as I said earlier, some of the particles are very sensitive to the acid dissolution, and also some of the sample it may slip through during the wet chemistry analysis. Due to these reasons, we can't predict exactly what happens in the acid dissolution technique. Thereby, XRD technique is a completely controlled process, and we can see the error bar limit also very less compared to the acid dissolution technique. And In my research, I have used the XRD direct decompression method to quantify and also to identify the reaction kinetics in an activated system, especially to determine the glassy content as well as reaction frequency. And coming to the third part of my today's presentation, it's about the strength point of view. How does various process variables influence the compressor system? And this is the key contribution to this research field. Then I have introduced a total reactive oxide ratios approach to produce stable fly ash based geopolymers irrespective of fly ash source without affecting its performance. And I'll try to explain this what I have done in this process. And generally, we use sodium silicate and sodium hydroxide are the alkali activators, or some of the researchers they have used potassium silicate or potassium hydroxide are the alkali activators to activate the flash. And if you use the sodium silicate and sodium hydroxide alkali activators based upon the sodium oxide and well as silicon dioxide content in the working solution, we used to call as the solution. And based upon those contents, they have determined the silica to sodium oxide mass ratio in the solution. And is the ratio they are reporting from past 2 to 3 decades, and whatever ratios are available in the literature or whatever ratios so far they have reported in the literature, those ratios are applicable for which type of fly ash they have used in the study. If I use the same ratio for another source fly ash, I will not achieve the same properties like what he has used in the study. It is a big drawback in the literature review. To overcome or to address this drawback, then I have introduced this total reactive oxide ratios approach. The total reactive oxide ratios I have determined based upon the total reactive oxide contents present in the activated mix. The activated mix is nothing but the fly ash contributes the reactive silica as well as reactive alumina to the system, and the sodium silicate as well as sodium hydroxide will contribute silica as well as sodium to the activated system. If the fly ash has the alkalis like potassium or sodium, those alkalis also we have to consider while we are calculating these ratios. And this is the total reactive oxide contents present in the activated mix. Based on these contents, I have determined the total silica to sodium ratio as well as total alumina to sodium ratio in the activated mixes. These are all the globalized ratios. It can be useful for any source of fly ashes, and it will give the proper results with respect to fly ash source. And to prove this point, I have carried out some of the experiments using different source fly ashes. I try to apply the what literature says like working solution ratios, and I have used my own ratios irrespective of fly ash source to prove this point, which ratios are important in this research field. And I will try to show all those results in the next coming slides. And overall, the total reactive oxide ratios are approach introduced to this research field, and these are all globalized ratios, and it can be applicable for any source fly ash. And coming to the what is the role of silicates on strength development in fly ash based binders? And is the compressor strength with respect to age. This is for fly ash B and it is for fly ash N. These are the source locations. And with the addition of is the values without addition of sodium silica, and which has about 13% of reactive silica. And once I have increased the reactive silica from 13% to the 19%, I can see a significant difference in the compressor strength at any particular time. With the 19% of reactive silica, I can achieve about 63 megapascals compressor strength ultimately. But in case of 13% of reactive silica, I can achieve about 32 megapascals compressor strength in the activated system. And due to this reason, the silicates are very important to achieve the ultimate higher compressor strength in the activated mixes. And coming to the what is the role of initial molarity? This is and also sodium content. Well, the researchers are using the molarity level is 18 molars, 16 molars, 14 molars, 10 molars, 8 molars, or they're using like significant higher concentration of molarity. And here the question is it really required to have like 8 molars, 14 molars, or 16 molars molarity in our alkali system? And that is the big question is have in front of us. Then finally we try to identify what is the role of molarity as well as sodium content in the activated mixes. And this is the x-axis represents the initial molarity and y-axis is the compressor strength. And this is with respect to years, the 3 days, 7 days, 14 days, as well as 28 days. And here the bracket, it represents the level of sodium content. And this is about 1.9 molars, and this is about, sorry, this is 1.2, and this is 1.9 molars, and this is 3.2 molars, and is about 10.5 molars. And as you can see here, after 7 days, increase the molarity from 3.2 to 10.5 molars. There is no much improvement in the uh, composition. And there is no much improvement in the compressor strength from 7 days to 28 days. It increase the molarity from 3 to 10.5 molars. But what the molarity or sodium content will do in the system? Increase the molarity, which leads to increase the sodium content in the activated mixes. And with the 4% of sodium content, which means about 3.2 molars, and you can see the color of the uh, one of the failed cube specimen. And with the 7.2% sodium content, this is about 10.5 molars 10.4 sodium hydroxide solution. The increase in the molarity from 3.2 to 10.5 molars, it's clearly enhanced the color change, but without affecting the compressor strength. The both the specimens we have achieved about 62 megapascals, but the only thing increase the molarity from 3.2 to 10.5 molars, and it will helps to change the color of the product rather than increase the compressor strength. Which means that we should have certain quantity of sodium content and also certain molarity in the system, rather than blindly adding 10 molars, 12 molars, 14 molars to the activated materials. And coming to the, this is another example of what is the role of molarity as well as total sodium silica to sodium ratio. As I said in the previous slide, this is 1.3 molars, so 1.9, and 3.2 are 10.5. And the lower molarity like 1.3 and 1.9 molars, we can able to achieve about 42 megapascals and 32 megapascals compressor strength ultimately. But in case of 3.2 and 10.5 molars, we can achieve about 60 megapascals at 7 days itself, but there is no much improvement after 7 to 28 days for increase the molarity from 3.2 to 10.5 molars. Then what's happening with the 3.2 and 10.5 molars in the active system? Then I have determined the unreacted glassy content and also the reaction product in the system. The fly ash, what the one we have used in this study, it's about 50% of 55% of glassy content present in this fly ash. And as you can see here, at 1.3 and 1.10 molars, we can see a steady decrease in the unreacted glassy content from 1 to 28 days. Whereas 3.2 to 10.5 molars, in case of 3.2 molars, you can see a rapid decrease from 1 day to 3 days, followed by the 7 days. But in case of 10.5 days, almost 40% of fly ash already dissolved between 0 to 24 hours. But in case of 3 molars, we even only 20% the glass is dissolved. But after 7 days, you can see the unreacted glassy content is the same as both 3.2 molars and 10.5 molars. And if you observe the reaction product content, from 7 days, there is no much difference in the reaction product content. It indicates that the 3.2 molars is more than sufficient to dissolve the glass present in fly ash. If we have the fly ash glassy content less than 60%, then there is no point to use 10.5 molars or higher molarity as literature says. Due to this reason, after 7 days, you can see the compressor strength is more or less same. Why? Because that already the glass is dissolved by 7 days, and both the 10.5 and 3.5 molars shown similar in glassy content and also similar in reaction product. And that is the reason both the mixes are shown similar in strength from 7 days to 28 days. And the compressor strength is directly proportional to the reaction product, and it's inversely proportional to the unreacted glassy content present in the fly ash. And coming to the what is the role of working solution as well as total react to oxide ratios in the activated system. Then to understand what is the role of working solution as well as total react to oxide ratios, I have chosen two source fly ashes named as A and B. And fly ash A, total silica to sodium ratio. The total silica to sodium ratio of fly ash A was applied to fly ash B, and fly ash A solution silica to sodium ratio was applied to fly ash B. And as you can see here, the total reactive oxide ratio mixes at any particular time, both the fly ash source are shown similar in compressor strength with respect to fly ash source. Whereas the working solution ratios, if I applied as literature says, the fly ash A solution ratio to fly ash B, you can see a significant difference in the compressor strength. Then results clearly illustrates that the total react to oxide ratios are important, are keen to produce similar in compressor strength respect of fly ashes, not the working solution ratios. Then I have tried the different ratios about instead of 3.06 as well as I have tried 3.82 as well as 4.5. And at any particular time that both the respect of fly ash source is shown more or less similar in compressor strength in the case of total reactive oxide ratios. But in case of working solution ratios, you can see a significant difference from working solution ratio from one source to the another source. Then I try to identify, I try to understand how does the dissolution mechanism as well as product formation will take place in these fly ashes. As you can see here, the total reactive oxide ratio mixes dissolve almost dissolved by 14 days, and thereby there is no much difference from 14 to 28 days. And most of the fly ash is dissolved by 7 days. But in case of working solution ratios, you can see a slow decrease in the what we can say like a slow decrease in the unreacted glassy content, and also more or less the both the results are shown in the more or less similar. The only thing is that when we are maintaining the total reactive oxide ratios, we have the higher in silicates and also we have the molarity is more or less high in compared to 3 molars. That is the reason we can able to achieve the higher in compressor strength in case of total reactive oxide ratio mixes. And if you compare with the reaction product content, irrespective of fly ash shows in various mixed proportions, and both the fly ash shown more or less similar reaction product content, which already replicates the compressor strength development in the previous slides. And coming to the product type, which type of product is formed in the total reactive oxide silica to sodium ratio mixes as well as working solution silica to sodium ratio mixes. And this is the SEM image at 10 micron scale. It alkali activated mix at silica total silica to sodium ratio is equal to 3.06. As you can see here, you can observe a dense portion all over the image and also a partially reacted spheres and also a completely reacted spheres here. This dense portion represents the reaction product, which means it's a sodium aluminum silicate gel. It is a gel. Then I try to understand and try to identify what are the elements are incorporated in the dense production. This is the dense production or the reaction product is responsible for the strength development. That is fine with me. Then what are the elements are present in this reaction product? Then I have carried out the EDAX analysis, as you can see in various locations. And all these locations, I can able to see the silica, sodium, alumina are incorporated toward this reaction product. Finally, I have classified as the sodium aluminosilicate gel is formed during the alkali activation process to the low calcium siliceous fly ash. And also I have observed in very few locations the calcium also incorporated in the system, but that is very nominal. Here the predominant quantities are, as you can see, the sodium, alumina as well as the silica. Then I can clearly illustrate that it is sodium aluminosilicate gel if you use the low calcium siliceous fly ash. Then here I have determined the silica to alumina as well as alumina to sodium ratio in various ratios. So these for total reactive silica to sodium ratio, and these the working solution silica to sodium ratio. As you can see here, if you compare both the working solution as well as total reactive ratios, the silica to alumina ratios are quite high in case of total reactive silica to sodium ratio, whereas working solution ratios shown lower in silica to alumina atomic ratio. That is the reason we are achieving the lower compressor strength in the working solution ratios, because it's required some more silica contents in the system rather than to reach the similar ultimate strength like other source flash. We have to balance those ratios and these quantities. Then only we can able to achieve the similar in the product as well as similar in the ratios in the system. Thereby we can produce stable flash-based geopolymers irrespective of fly ash source. And I have mentioned that the total reactive oxide ratios are keen to produce similar in compressor strength. Then what is the optimum reactive ratio? Then I have varied the silica to alumina ratio from 1.8 to 2.3 and also the alumina sodium ratio from 2 to 2.5. And these with respect to age, these at 1 day, 3rd day, and 7, 14, 28 days. And you can see the increase in the ratio from 1.8 to 2 is clearly enhanced the compressor strength from 1.8 to 2. But increase in the ratio beyond 2, there is no much improvement in the strength after 7 days. We can see a reduction in the compressor strength at early stages at 1 day as well as 3 days. But after 7 days, there is no much improvement or reduction in the compressor strength, increase the ratio beyond the 2. Thereby, the optimum silica to alumina ratio is equal to 2 is the producer stable fly ash based binders irrespective of source. And coming to the alumina to sodium ratio, increasing the ratio beyond 2 does not help much to improvement of overall compressor strength from 7 days to 28 days. Then the optimum value will be 2. The alumina to sodium ratio will be 2 as well 2.5. Maybe you can use less than 2.5 to produce optimum value. And coming to the microstructure in the various total reactive oxide ratios at various days, this is the third day, and this is the 7 days, this is the 28 days, 10 micron scale is a 10 micron scale, and this is at 30 micron scale. At 10 micron scale, you can see the cyanospheres, it's dissolving. It indicates that at third days, the cyanospheres are dissolving, and also already the product is formed here. These particles are dissolved, and the formation will take place around this area. But in case of 7 days, you can see the cyanospheres are completely dissolved, and some of the cyanospheres, you can look at here, the sphere is dissolving and the product is forming around the cyanosphere. And almost the completely dissolved spheres I can observe at 7 days. But in case of 28 days, we can see a dense product over the image, and also almost or completely dissolved the cyanospheres I have observed over the image. And if you look at these results here, and I have tried to identify what are the elements are incorporated in this reaction product, and all these locations, the silica, alumina, sodium elements are incorporated. Finally, I have classified, say, sodium alumina silicate gel. Then I have also observed some of the new crystalline phases when I stated in the during the product formation. Those crystalline phases, what are those crystalline phases? I have tried to identify with this microstructure, and I have observed like a thermal based, like we can see thermocol based whitish dot particles over the image, and I have carried out the index analysis on these type of particles, and these are all chabazite based particles, sodium based geolites. And also I have observed small needle types, and also very big needle type of new crystalline phases I have observed in my various alkali activated mixes. And these small phases and these what we can say that big needle shaped particles are classified. All these things are is a sodium based geolites, because if we have the excess sodium which leads to formation of geolites in our system, we have to optimize those mixes as well as. And coming to the role of reactive alumina content as well as microstructure. So far I'm talking about the silicates and all those things. Now, what is the role of reactive alumina content? As the reactive alumina, we have to completely rely on the fly ash source, because we can't add the reactive alumina externally. Why? Because it is a very expensive element, and we have to we have to think about the economical point of view, and that is the reason we don't want to use the reactive alumina externally. And also, still this research is going on this particular component, and we don't know which type of format is available in the fly ash, and also uh, the local real time locality, and still the research is going on this particular component. And to understand what is the role of reactive alumina content in fly ash based mixes, then I have used two different source fly ashes. The one fly ash is very rich in reactive alumina, it's about 16%. The another fly ash is reactive alumina is about 8%. In both the mixes, the reactive silica, the total reactive silica, the water to binder ratio, and the sodium contents are same. The only variability is the reactive alumina content. Then the ratio is also same. Then if you, as you can see it here, increasing the reactive alumina from 8% to 16%, you can clearly see there is a significant improvement in the compressor strength starting 1 day to 28 days. With the 16% of reactive alumina, I can able to achieve about 72 megapascals compressor strength in our system. But with 8% of reactive alumina, I can achieve about only 28 megapascals compressor strength in our system. And if you want to use it practically, if you want to produce the high grade concrete, then we have to choose the higher reactive alumina content fly ash. If you want to produce the low grade concrete, then you have to choose the lower grade of reactive alumina content of fly ash to use it for the various construction related applications. Then this is the microstructure of the high reactive alumina content mix. As you can see, a dense portion over image, and also completely reacted SPS, and all this dense portion is rich in sodium aluminum sulfate. Overall, whenever we're using the low calcium fly ash mixtures, the ultimately the product is the sodium aluminum sulfate gel, and the silica to alumina and all sodium is the majorly incorporated in this product, with a very tiny portion of calcium will be incorporated in various locations. And coming to the again, I would like to prove what is the role of molarity in these locations. And if you increase the molarity from 3 molars to 5 molars, I didn't see much improvement in the compressor strength. If you are able to maintain the total reactive oxide ratios, then this is the compressor strength and this is the reactive classic content and also the reaction product content. The molarity will not play a major role on strength development. The molarity will help to dissolve the glassy particles in our system. Yes, literature says the increase the molarity will improve the compressor. No, the molarity will helps to dissolve the glassy particles in the system. Thereby, whatever reactive species is available in our system, those reactive species will precipitate. It will lead to formation of sodium aluminum sulfate gel in our system. And coming to what is the role of water to binder ratio, and here I have used two different water to binder ratio. Here the bind is nothing but typically we'll use water to cement ratio. Instead of cement, I have used the binder here. The binder is nothing but the binding material. It's a fly ash as well as alkali activators. And if you increase the water cement ratio from 0.19 to 0.27, you can see clearly reduction in the compressor strength at any particular time. And why it's happening in these two mixes? Because these two mixes I have maintained the molarity, total reactive oxide ratios, and the contents and everything is same. Only variability is the water bind ratio. Then I have determined the specific surface area of these two materials at 28 days. With 0.19 water to bind ratio mixes have the lower in specific surface area, whereas with 0.27 the specific surface area is about 17.26 meters square per gram. Due to that reason, the specific surface area also clearly plays a major role on the strength development, but we should not use the higher water binder ratio if you want to achieve the higher compressor strength in our flash based binder. Still, we are working on this particular component currently. And coming to the what is the role of curing temperature? Yes, the literature we used to use 60%, 60 degrees Celsius, 85 degrees Celsius, 105 degrees Celsius. Here the question is it really required to use the higher elevated temperature? Then I have used two different curing temperatures, 60 as well as 85 as well as 40 degrees Celsius. As you can see, the compressor strength development. In case of 85 degrees Celsius, I can achieve 100% compressor strength by 7 days. Thereby, there is no much improvement in the compressor strength. In case of 60 degrees Celsius, I can see a steady increase in the compressor strength till 14 days. Thereby, I can achieve the maximum strength by 28 days. But in case of 40 degrees Celsius, the strength is steadily increasing till 90 days. In case of lower curing temperatures, we have to wait much longer curing time to achieve the similar compressor strength like other curing temperatures. When if you are able to maintain the total reactive contents, total reactive oxide ratios are same, you can see these type of trends. Then if you are using the working solution ratios, then you will not achieve the compressor strength at 40 degrees. And this is with the pure fly ash system. We have not used any slag and also we have not used any additives. We would like to use the only pure fly ash, thereby we can able to control the other parameters. Then if you look at the unreacted glassy content and also the reaction product content, the compressor strength is proportional to the reaction product and also inversely proportional to the reacted glassy content. And all these three mixes, everything is same, only variable is the temperature. We have various three curing temperatures. And at 40 degrees Celsius, you can see the dissolution is taking place very slowly. In case of 16 to 85 degrees Celsius, you can see the dissolution is completely by 7 to 14. And also again, okay, we try to identify which type of product is formed in this curing temperatures. If you increase the temperature from 40, 60, and 85, then the silica to aluminum atomic ratio is sure more or less similar trend like compressor strength. And also I have used another tool, FTIR, to identify whether once we have varied the curing temperature 40, 60, 85, there is any possible to change in the bandwidth. Then as you can see here, this is the pure fly ash bandwidth is about 1073. In case of alkali active mixes, then we can see there is no much. So the bandwidth is slightly it's a lower wave number, and overall, this change in the bandwidth is this is the representative formation of Nash product, and this is the glassy portion of the fly ash. And it is also evident by our SEM results. It is the product type is clearly say, sodium aluminum silicate gel, and the silica alumina is incorporated in the structure. And also we have tried what is the role of curing the time at two different curing temperatures. And this is the schematic representation for time we have used it in our research. We have used two different curing temperature, 25 and 60 degrees Celsius. And the F1 indicates we have cured the samples one day at 25 followed by 60. And F2 indicates 2 days at different intervals, 2 days at 25 followed by 60 at the remaining curing temperatures. And to see like whether there is any possible to change in the morphology or possible to change in the product type or possible to change in the glassy dissolution. And would like to identify what's happening if we change the temperature, because we can see when we are using the real-time applications, we can see a clear difference in the daytime as well as nighttime temperatures in our locality. And as you can see here in the compressor strength, and this is the baseline mix, the F is completely cured at 60 degrees Celsius. And as you observe here, and F as well as F2 as well as F5 as well as F1, all these three curing temperatures. Whenever we are raising the curing temperature, you can see there is a rapid increase in the compressor strength. But in case of F10 as well as F7, the fly ash cured at 60 degrees Celsius at 7 days, followed by 25 degree Celsius. And after seeing all these results, whenever using the concrete, the fly ash alkylated system should be cooled at 7 days at a particular 60 degrees Celsius. Then only you can able to achieve the maximum compressor strength without increasing the curing temperature. And if you want to use the precast applications, how much time we have to cure at the elevated temperature. And if you are able to use that pure fly ash, and if you're able to optimize the mix proportion, and if you cure at 7 days, that is more than sufficient to achieve the maximum compressor strength in your system. Then I have cured at 7 days, then followed by I have achieved the reaction is progressing remaining days, and I have achieved about 72 megapascals compressor strength in our system. And the similar trend I have observed in unreacted glassy content as well as reaction of product content. Whenever I have increased or decreased the temperature, I can see a drop in the reaction product as well as I can see a drop in the unreacted glassy content. And also the product type, we try to identify which type of product is from the system, and then all the locations I can see only the silica, alumina as well as sodium incorporated in reaction product. Even though we have changed the temperature from 60 to 25 or 25 to 60, the product content is same. And this is another interesting finding we have identified in our research. How does the product type clearly influence the ultimate strength? As I said so far, the silicates are important and also the reactive alumina content. How does the silica to alumina atomic ratio in the structure ultimately influence the ultimate strength? I have designed the two mixes. I have named as method 1 and method 2. Sorry, the same mix. I have used the two methodologies. And one set of samples I have queued till 24 hours at 27 degrees Celsius, followed by 60 degrees Celsius at 28 days. And the method 2, I have I have cast the specimen. I have continuously queued at 60 degrees Celsius till the achieve the till 28 days. Then I have determined the compressor strength at 28 days. I have determined the reaction product content, and also I have determined the silica to alumina atomic ratio, and also I have determined the unreacted classic content. And the silicon to alumina atomic ratio I have placed on the x-axis, and the left side of y-axis represents the compressor strength, and then right side is the reaction product content. If we compare the method 1 method 2, the mix proportions and everything is same. The only variability is the curing condition. How does the product type? And the method 1, the one I have cured till 24 hours at 27 degrees Celsius, followed by 60, then I can see the silica to alumina atomic ratio is about 2.84. But the one I have cured continuously at 60, I can see about 3.24, which means increasing the silica to atomic ratio from 2.84 to 3.29, I can achieve about there is a increase in the compressor strength about 10 megapascals, which means the silica to alumina atomic ratio in the microstructure it clearly influences the ultimate compressor strength of our fly ash based geopolymer. And if time permits, maybe I would like to show some of our trials. With all this background, then we have carried out some of the concrete trials at our laboratory when I was at IIT Hyderabad. And I have designed two mixes. The mix one is 30% of binder. The binder is nothing but fly ash, sodium silicate, as well as silica, sodium, and also water. And aggregates is coarse aggregates as well as fine aggregates. And the another the mix two is 40% of binder and 60% of coarse and fine aggregates. There are weight fractions. And here's the few we have conducted a few workability trials at our laboratory. At 70% of aggregates, it's about 60% of further I have divided 60% of coarse as well as 40% of fine aggregates. And this is the slump I can see it immediately once I have casted, and once we lift the slump cone, I can able to see 120 slump. And after 3 months, you can see the slump is completely collapsed. And similarly, if we change the proportion of 50% coarse aggregates to 50% of fine aggregates, and after 3 minutes, I can see the slump value about 230 minutes. And similarly, at 60% of aggregates, once we have lifted the slump cone, then I can able to see a spread like this. And the value is somewhere near to 450 slump after 3 minutes. That's 60% of aggregates. And after 3 minutes, this is at immediately 450 and this is at 3 minutes. It is about 60% of aggregates at 60% of coarse aggregates as well as 40% of fine aggregates. These are all like we have tried few of the trials. We have varied the coarse aggregates, we have varied the fine aggregates, we have the varied the total aggregate content 70% and the 60% to see whether this fly ash with geopolymers we can use like self-leveling concrete or not. And these are some of the laboratory trials actually we have conducted. Maybe I don't know why it's not that coming. Let me take my. And if you, yes, yeah. See, you can if you increase the water to geopolymer binder ratio from 0.19 to 0.25. So these are all mixes is the 0.19. If you increase the water binder ratio to 0.25, you can see the how does the mix looks like. It's a very cohesive and also it's a more workable, and there is no point to add additional superplasticizer or add mixture because the fly ash itself has spheres and it will rotate like very nicely and will be leads to the self leveling of concrete. And these are the mechanical properties we have determined, the 30% of binder and 40% of binder. With the 30% of binder, 70% of aggregates, I can achieve about 72 megapascals. With 40% of binder, I can achieve about 62 megapascals strength. In case of split tensile strength, the similar trends we have observed here. And then finally, we have captured the images and whether the bond between the aggregate is failing or the bond between the paste is failing. Then you can able to see finally whatever paste we have developed here is very strong bond. The paste is not failing. We can see the aggregate fracture you can observe in various locations, which means the bond between the aggregate as well as paste is very strong. The conclusions and also the outlook of the overview. If you ask me to give an overview, as I said, our intention is we would like to improve the fly ash utilization in the cement and the concrete sector. And if you're able to understand the reaction of fly ashes, is an important step towards improving the qualification of the use of these materials. And if you rather than 30%, if you're able to increase the 10% of fly ash in our cement and concrete sector, then we can able to minimize the 18 million tons of fly ash per year, rather than dumping in a few locations. We can utilize for our efficiently because we are using the fly ash in various applications, but how efficiently we are using the what purpose, because our intention is we would like to use in cement and concrete sector. Thereby we can able to reduce the carbon dioxide footprints in the atmosphere if we are able to utilize these fly ash in a right way. And as researchers as well as scientists and as a all of our different industry people, see, our goal is as a civil engineer and also the material science expert, as the chemistry experts and all those things. As a civil engineer, if we are able to predict exactly what happens between the material property as well as the performance. As engineers, we used to worry about the performance. Okay, this is the compressive strength I want, this is the fracture behavior I want, and all those things we used to worry how durable our material. As a engineers, we are able to predict exactly what happens in a fundamental level, or like a fundamental behavior of the material. How does the material behaves in, once we have received from some industry? Not only flash, any other material, and how does the particular material behaves once we have received from the industry. You are able to predict exactly what happens and what are the elements and what is the orientation of elements, what is the reactive potential and non-reactive potential. We have to do the thorough characterization. Thereby we can able to predict what happens if used in our cementitious application. How does the microstructure looks like? How does the phase formation? Whether the product is stable or not, or the product is changing its morphology over a period of time, and also how does the kinetics will take place in the system. And if you're able to focus on these particular locations, then you can able to predict exactly what happens in a structural level. That is, we have to establish the link between the material property to the performance of the various structural point of view. And thank you very much. If we have any questions, we open it.
Yes, participants are welcome to ask any questions. I am very grateful that Dr. Bhagath Singh has shared in-depth knowledge about activated this geopolymers and production of geopolymers, and he has amply illustrated the use of sophisticated instruments like SAM, XRD, and talked about and has set the pace for the microstructure of concrete in depth. The next talk is on the microstructure of concrete. So I request participants to ask any questions. In between, some of the experts of the country also joined. I think I could see Vijay Kulkarni ji. He has left now, and some other Indian Concrete Institute members. They have joined in between, and with us again, three expert resource persons of this FDP are with us: Dr. Hegde ji, Dr. Kyadas Narayanan ji, Dr. Bhavna Tripathi ji. So I welcome them also. Any participant may ask query. No questions asked. Dr. Mahipal, you have been active. Any questions? Dr. Mahipal also seems to have left just now. One question has come. Dr. Bhagat Singh ji, if you can see the chat.
Yes, we can use the metacalin as well as instead of fly ash. The metacalin, if you use the metacalin, maybe the similar structure like the silica and alumina, then what as per my previous experience with the metacalin, and we can able to produce the room temperature based geopolymers, but our intention is we would like to use the industrial waste material. Like how can we use the metacalin? Ultimately we are getting from the clay, that is also naturally occurred material, and why don't we use the industrial waste material to use it in our cementitious applications? Yes, for your question, yes, we can use the metacalin. The structure and then the atomic orientation is more or less similar like fly ash. Compared to the cost comparison, and so we have not carried out at the concrete level as per the binder point of view. Yes, we have conducted, and it is much cheaper than the considering fly ash as a free of cost, and we have considered only transportation, and it is coming under 150 kgs, 150 rupees per bag of cement. Considering the other fly ash is free and it's a very near to our industry. Pumic powder, yes, I don't have no idea about the pumic powder. Sorry. Maybe if you can able to elaborate somewhat, then I can able to see.
Sir, I have a question.
Yes, sir.
So is there any low-cost alkali activated solution alternative that to be used in geopolymer production?
Yes, sir. Actually, currently we are working on it now. See, our intention is, our question is maybe we'd like to produce the room temperature geopolymer. That's what your question is.
Yeah.
Yes, currently we are working on it, sir, now. Because if you're able to add like about 2% to 3% some additives, yes, we can able to produce the room temperature geopolymer.
Okay, thank you, sir.
Our friend Rajamaneji has been propagating room temperature geopolymer production. Dr. Bhagat Singh ji is more conversant with that. Uh, uh, Dr. Rajamane and some people at Jadavpur University have also worked in that area.
Yes, sir. Yes, sir.
One question is regarding Indian standard for geopolymer.
Yes, I think still we are working on it. We don't have proper standard for geopolymers as per our Indian standard. The shrinkage in geopolymers concrete is less than the normal concrete. Yes. So the shrinkage, we have conducted a preliminary studies on the shrinkage, and then yes, when compared to the normal concrete, it's very less. Because we can able to see the shrinkage in the first few days, first 3 days. Then once the reaction is completed, then there is no more shrinkage in our system. Because during the geopolymerization process, most of this water will come out from the system. In case of normal concrete, it will hold the water. Here, the water molecules is not a part of the structure. Due to that reason, the geopolymers is not shrinkage is not a problem in geopolymers. Geopolymer setting time, it depends on the various factors. Depends on the temperature, and it depends on the, if you are able to use the additives, then you can able to cut down the setting time also. Geopolymer as a rural technology is possible. But yes, some more field studies should be carried out, because we have just started on the concrete trials. Then once everything goes well, then we'll try to implement in various locations. Yes, alkali activated materials and geopolymers. As per the Davidovitz definition, the geopolymers is defined as a sodium aluminum silicate gel. We can't call it as complete all the alkali materials are geopolymers, because as per his definition, he patented the geopolymers. If it is the sodium, the product is the sodium aluminum silicates, then we can call it as a geopolymer. Otherwise, he said we have to call it as a hybrid binders. We should not use geopolymers terminology there. And can we recommend agriculture waste used in the pillar material geopolymer concrete? Yes, we can. We can recommend agriculture waste also, but I don't know what are the elements are present in this material. We can use any materials which has the rich in way, whatever the elements I have shown in the slides. Uh, the steel more bond to geopolymer concrete than it does ordinary core. I don't have ideas. We have to work on towards this. Can sodium metasilicate work instead of sodium silicate? Yes, we can work, but we have to know what is the composition of this sodium metasilicate. See, currently, the limitations of geopolymer concrete is, so we can use it like normal conventional concrete. The only thing is that now we require slightly higher temperatures to get it set, as well as for geopolymerization process. And if you're able to cut down the room temperature, then we can able to use it for normal conventional concrete. I hope I have answered a question for Dr. Manisham. Manoj Kumar, is it being used commercially? No. Currently, we have not used anywhere. We have carried out the preliminary studies. We have tried to identify the microstructure and all those things. The concrete point of view, we are working on now. We are working on it now. We would like to apply in few locations in rural areas. Can you share some resources for reference? Like what exactly you want? If you could have tell me like what exactly presentation. So presentation is some of the data is not published, that I can't share. Maybe you can go through my publications.
if there are no further questions, may I thank Dr. Bhagat Singh ji for
Yeah,
a very lucid presentation. And of course, as he has rightly shared that some of the research which he has shared in his slides are even not published till now. Some of the publications which we saw during the presentations have been published in Cement and Concrete Research Journal, which is the foremost journal of concrete research, and particularly the material properties. So everybody can see the published literature, and somebody has written that B.V. Rangan sir, of course, B.V. Rangan sir has been in the initial stage at the geopolymer concrete development. So definitely, Dr. Bhagat Singh ji's publications are available on Google Scholar. Somebody has written details of your present publications, so we can always refer to them. So thank you very much, Dr. Bhagat Singh ji.
yeah, yeah.
I
Thank you.
extend my warm thanks to you on
Thank you.
behalf of the Rajasthan Technical University and on my personal behalf, and look forward to further hearing you in coming years and coming times.
Sure, sir.
I
Thank you very much for inviting me for this presentation.
thank you, sir. So it is my proud privilege to welcome Dr. B.K. Vendan from SVNIT Surat. Welcome, sir. Are you able to hear me?
Yeah, I am able to hear you, sir.
So, as I was talking in the morning, he, along with Professor Bhattacharya, has done marvelous work in the microstructure of cement and concrete. So, we are fortunate to have him as resource person, as a speaker in today's session. I welcome him and invite him to start his presentation. You may present, yes, sir. Your screen is coming, sir.
Yeah. Good morning to one and all. First of all, I would like to thank Professor Praveen Kumar Agarwal for giving this opportunity to present my lecture on this. So today I am going to present my lecture on microstructure of fly ash blended cement-based materials. Whether my screen is visible?
Yes, sir. Yes,
Okay,
sir.
Okay, fine. Okay. We know that concrete is the most consumed material in the world. Okay, if you look at the evolution of the concrete, it is starting from lime mortar, Surkey mortar to plain cement concrete to reinforced concrete to free stress concrete, and nowadays we are all talking about the high strength concrete, high performance concrete, and also ultra high performance concrete, and all we are talking. Even if you look at the ingredient of the concrete, so in olden day concrete, it consists of 4 ingredients like cement, fine aggregate sand, coarse aggregate, and water. But in the modern day concrete having 6 ingredients. What I mean to say, it apart from these 4 main ingredients, we are also adding the mineral admixtures like fly ash, silica fume, and other things. And also we are adding the chemical admixtures like superplasticizer and other chemical admixtures. That's why the modern concrete consists of 6 ingredients. Okay. Even nowadays it is quite common. Whenever we want to achieve the high strength concrete or high performance concrete or ultra high performance concrete, it is mandatory. We have to add some of the mineral admixtures like fly ash or GGPS or some other material like silica fume, metakaolin. Those kind of materials we are adding. Even nowadays it is quite common. Even people are started using this PPC and PSC cement instead of using the ordinary Portland cement. They are going for the Portland Barcelona cement and Portland slag cement. Okay, and quite often we come across the literature also. So whenever we are having this kind of new materials, whenever we are adding this fly ash or silica fume in the cement system, we are getting the high strength and also we are getting the more durability. So there is some pore refinement is happening. That's how we are getting the higher strength and a better density also we are getting, and we are getting the more durability also. So, but have you ever think how it is achieved? So, what is the chemical reaction behind this? So, only we just came to know it is improving the strength and durability. But actually, inside what is happening? That's what I am going to discuss in this lecture. Actually, the highlight of my lecture is I would like to say, actually, whenever we want to determine the compressive strength of the concrete, what we used to do, we used to cast the concrete cubes of 15 centimeter according to the Indian standard, and we will cure it for 28 days, and again we will go for the compression test. That's how we are getting the 28-day strength of the concrete. But if suppose you want to know the strength of the existing structure, what we used to do, we used to go for some non-destructive tests like a rebound hammer or ultrasonic pulse velocity. Those things we used to do, but it is not very reliable. Only approximately we can get some idea. But even if you are not relying on those, then we used to go for the semi-destructive test. That is the core test. We used to take a core and we used to test it, and we can calculate what is the equivalent cube strength. So all these kind of tests, actually, some of the things are time-consuming, some of the things are not reliable or partially reliable. So is there any other ways and means to determine the compressive strength or the durability properties? Is there any other way? So can we determine this compressive strength, permeability or hydraulic diffusivity through the microstructure? Is it possible? That's what I would like to ask you. Is it possible? My answer is yes. We can determine the compressive strength. We can predict the compressive strength. We can predict the permeability. We can predict the hydraulic diffusivity. That's what I am going to discuss in this lecture. Okay, it is possible. We need not wait for 28 days. Within a few minutes, we can able to predict the compressive strength through microstructure. That's what my entire lecture is going to cover. Okay, so in my lecture, my flow of presentation should be like this. First, I am going to introduce what is the microstructure, and also I am going to talk about the microstructure of the cement-based material, and I am going to introduce one instrument called a mercury intrusion porosimetry, and also going to talk about number of case studies. At least 3 case studies I am going to study. I am going to discuss whatever I studied that I am going to discuss, and also I am going to tell about how to do the theoretical modeling of the pore size distribution parameters and what is the applications, and also some conclusion from those case studies and some of the publication related to that work and references. That's what I am going to discuss in this entire lecture. So let us first talk about the microstructure. So whenever we want to achieve the high strength concrete or high performance concrete, it is mandatory we have to add the fly ash or silica film or some other pozzolanic material or cementitious material we are mixing. If you are adding those things, what is happening inside? Actually, there is a pore confinement is happening. So when we talk about pore, so we should know what is pore structure. So the very first question, whenever I am hearing pore structure, first question pop up in your mind, what is pore? What does that mean? So pore is a flaw or defect in the cement-based material. Even in the layman language, I can say it is a minute hole or void. Inside the concrete, what it consists of? If you see the concrete at the macro level, it is a two-phase material. We can consider it as a two-phase material. The aggregates are dispersed on the cement-based matrix. So that's a two-phase material. But if you look at the micro level, what it consists of? So if you look at the micro level, you can find pores and porosity. That is the inside concrete. So generally, the failure of the cement-based materials are happening due to the development and propagation of the cracks. Even the failure is starting from where the largest pores are concentrated. So that's why the strength of the cement-based materials are generally governed by the porosity and pore sizes. That's why we should know the pore structure or the microstructure of the concrete or any cement-based materials. Okay. So here you can see this diagram. I can tell you what are the different type of pores are there. You can see there are some larger pores, there are some small pores, and there are some pores are connected to the surrounding, and some pores are trapped behind others. Okay, actually it is very magnified. Actually we cannot see the pore through the naked eye. Okay, we need some sophisticated technology, then only we can able to see this. This is magnified to certain magnitude. That's why we can able to see this thing. So just for understanding this, I magnified this thing and I want to explain this. That's why this is a magnified view. Okay, so there are so many different type of pores are there, and among the pores, the interconnected pores are most vulnerable thing. So because that is only related to all the durability kind of problems. Okay, so how to characterize the pore structure of the cement-based material? So generally, the pore structure can be characterized by number of parameters. One is the porosity. So porosity we can easily define. That is the volume of void to the total volume. And again, hydraulic radius. This is another property one can determine. That is nothing but cross-sectional area of the pore to the perimeter of the pore. And another thing, the specific surface area. That is the specific surface of the pore we can determine. And threshold diameter or critical diameter of the pore also we can determine. And the last thing is the pore size distribution. So okay, I am mainly going to focus on the pore size distribution. So I am going to characterize the cement-based material based on the pore size distribution only. So let us see what is the pore size distribution. What does that mean? So pore size distribution means how the pores are dispersed in the cement-based material, how the pores are distributed in the cement-based materials. Okay, generally there are two types of pore size distribution is there. One is cumulative pore size distribution, another one is the differential pore size distribution. If you plot a graph between cumulative pore volume in cc by cc, that is cubic centimeter per cubic centimeter versus pore radius, then it is called a cumulative pore size distribution. If you plot a graph between minus dV by dLNR versus LNR, that is called a differential pore size distribution. These are the two different type of pore size distribution. Actually here just we are seeing how the pores are distributed in the cement-based materials. Okay, so you can also see this figure. It would be very interesting. You can understand also what I am going to discuss the entire lecture. Okay, so you try to understand this. If you are understanding this, then only it is possible to go for the further slides also. So you can see the picture. There are number of pores are there. Actually, maybe you can consider this is at the early stage of the hydration. So there are a number of pores are there. You can see, and the distance between the pores also there. Now I am going to talk about the entry radius. That is the pore radius that I am calling as R.5, or I can say it's a mean distribution radius. And D is the dispersion coefficient. That is nothing but the distance between the pores. So, okay, at the early stage, it should be like this. The pore sizes are very big. It may be coarser size. Okay, over the period of time, what will happen? There is a substantial degree of hydration will take place. So, automatically the pore sizes will reduce. The more and more CG will form. The size of the pore size will reduce. So, R.5 size will also reduce. But at the same time, the dispersion coefficient value will increase. Okay, so there are a lot of research has been done on this. Actually, we are the pioneer in this research also. Professor Bhattacharya and Patil has done some work on this cement-based material, and they found that pore size distribution is governed by three parameters. One is permeable porosity P, and R.5 is the mean distribution radius, and D is the dispersion coefficient. So I am clearly explaining you here what is R.5. R.5 is a pore entry radius, and D is the dispersion coefficient, that is the distance between the pores, and P is the permeable porosity. If you know these three parameters, and you can able to model these parameters as a simple mixed result factors like water cement ratio, curing age, and mean cement particle diameter, then it is possible to determine the pore size distribution parameters. Once you determine the pore size distribution parameters, it is also possible to predict the compressive strength, and also you can predict the permeability. So everything I am going to explain one by one. Okay, so now it's clear. I think R.5, D, and what is permeable porosity, everything is clear from this. So why we have to study about the pore structure characterization? Because nowadays, the last few decades, the concrete technologies focus their attention towards the microstructure. So actually the microstructure influencing the long-lasting service life of the structures. Because what is happening? So even though we are designing a structure, so before reaching its design life, the structures are showing some distress or deterioration. So until if you understand the microstructure, we cannot increase the service life of the concrete structures. So that's why we have to study about the microstructure. And generally, the strength and durability of the cement-based products are governed by the microstructure only. Okay, so and even in the microstructure, the pore system and porosity are the main things. Actually, those two things only playing a decisive role in influencing the physical and mechanical properties of the concrete. Okay, the pore structure of the cement paste mainly governs the physical and chemical resistance against the aggressive environment, strength and thermal conductivity. Okay, apart from that, ITZ, this is another important parameter, that is interfacial transition zone, that is the space between the cement matrix to aggregate, that also coming in this microstructure. So one has to understand the microstructure, then only we can improve the long-lasting service life of the structure. Because nowadays we are bringing a lot of new materials and we are mixing in the cement matrix. So we should understand the microstructure, how it is going to do the confinement of pores, and how it is making a impermeable nature, and how it is increasing the strength and durability. Everything we can understand through the microstructure only. So let us discuss what is microstructure of the cement-based material. So if you take the cement with the water, so let's say the high density cement particles react with the low density water, forming the intermediate density of hydrated products. Apart from hydrated products, it is also producing some pores and porosity. Okay, so still I can say in a simpler way, the cement consists of 4 major components, as we are all aware about it. So tricalcium silicate C3S, dicalcium silicate C2S, and tricalcium aluminate C3A, and tetracalcium aluminoferrate, that is C4AF. These are the four main components in the cement. Once you add the water, what is happening? The very first and prompt reaction is the C3A will react with water to form the C3AH6. That is called a hydrated tricalcium aluminate. Otherwise, I can say it's a flash shed. Okay, so actually it is not desirable. That's why what we used to do, generally we used to add the gypsum. The manufacturing of the cement process, the manufacturer is adding the gypsum of 3 to 5%, because if gypsum and water is there, the C3A is having more affinity towards the gypsum than water. That's why the C3A will react with the gypsum to form the calcium sulfoaluminate or ettringite. Okay, again it is not a stable form. Again it is converted to monosulfate. Again it is converted to AFT, AFM phases. Okay, after that the C3S and C2S component is reacting with the water to form the CHA gels and also calcium hydroxide. The calcium hydroxide actually giving the alkalinity to the concrete, and the CHA gels are actually contributing the strength. Okay, so during this hydration process, apart from this hydrated product, we can also find a number of pores and porosity. So there are two pores are very popular. One is the capillary pores. The originally water-filled spaces unoccupied by the expanding cement gel is called the capillary pores. The capillary pores are having the size of around micron sizes. So we can also call the capillary pores as the micropores. And there are some other pores also forming in between the CHA gels, that is called the gel pores, that is having the nanometer sizes. We can also call gel pore as a nanopores. Apart from this, there are two types of air voids is possible. One is air entrained air voids, another one is air entrapped air voids. So even sometimes we are also adding the air entraining admixture to avoid the freeze and thaw effect. Okay, so all these things actually constituting the microstructure of the cement based material. Okay, the microstructure consists of all these things. Okay. This is what I discussed earlier. So now you can see this picture. Actually, this is taken from the concrete structure and properties of the Mehta book. Okay, here the transition zone is shown. Actually, it is between the cement matrix to the aggregate. The space between the cement matrix to aggregate is called IT is the transition zone. And the capillary pores, that is a larger pore sizes. I also told it is a micro pores because it's having the micron sizes. These are all interconnected, so that's why it is very vulnerable for durability point of view also. So these are all the pictures I have taken from the concrete structure properties and materials by Mehta. Okay, and here another picture. This is also taken from the same book. Here you can see the cement unhydrated cement particle is shown. The right hand side picture you can see the unhydrated cement particles, and also what is the CHA gels are forming around the unhydrated cement particles. Okay, there are some gel pores are there. So the gel pores are having the size around 0.5 to 2.5 nanometer. That's why I call the gel pores are nanopores. Okay, and used to occupy around 28% volume of the CHA gels. And there are some big pores are that is called a capillary pores. So those pores are having in the micrometer sizes. That's why I also call the capillary pores are micropores. You can see the sizes varying from 10 micrometer to 1000 nanometer, and even up to 5 micrometer. Okay, you can find. Okay, and also you can find some hexagonal crystals of calcium hydroxide. Otherwise, you can say it's a Portland type. Actually, this is only giving the alkalinity to the concrete. That's why initially concrete is having alkalinity. Even if you see the concrete alkalinity, it is varying a pH around 12 to 13.5. A good concrete is having the pH 12 to 13 point due to this presence of the Portlandite, which is liberated from the primary hydration reaction. Okay, and here you can see some backscatter electron images. So I would like to explain better way. Okay, so here there are 4 images are shown: A, B, C, and D. So the image A, that is the actual backscatter electron image. You can see the image B. So it is the binary image of the unhydrated phase. So actually the hydrated things are in white color and unhydrated things are in black color. And if you come to the image C, that is the binary image of the pore space. The pores are in black color, the rest of things are in white color. If you come to the image 4, that is the polygon image of the pore features. Actually the pores are in polygon shape, so rest of things are shown in the white color. So that's how we can able to differentiate what is pores, how it is looks like inside the concrete. So those kind of idea you can get it from these backscatter electron images. Okay, so once you talk about the porosity and pore size, actually this is only contributing the strength and durability of the cement-based materials, then how we can measure the porosity and pore sizes? If you want to measure the porosity and pore sizes, there are so many methods are available. One is fluid displacement method, helium pygnometer method, capillary condensation and adsorption desorption isotherm, small angle X-ray scattering method, scanning electron microscope, nuclear magnetic resonance or NMR, AC impedance spectroscopy, mercury intrusion porosimetry, backscatter electron images. These are the different methods are available. Among this method, mercury intrusion porosimetry is the most popular. As soon as I say MIP is the most popular, a question pop up in your mind. Why it is so? Okay, because MIP can able to measure 1 nanometer to 200 micron sizes, and also it can able to produce the reproducible pore sizes, and the resistance offered by the cement-based material to the external agencies are governed by the pore entry radius rather than the true internal radius. Actually, MIP can able to measure the pore entry radius, and also it measures the permeable porosity, which covers most of the interconnected pores, which is having a direct relevance on the durability. And again, MIP can able to measure the, so during the extrusion intrusion can measure the here interconnected pores are very important. That is only related to all the durability issues. Okay, if you are having interconnected pores, then only problem will go aggressively. If suppose we are having isolated pores, there is no problem at all. Okay, so once if you are having interconnected pores, all the durability related issues are related to the interconnected pores. So this is the only instrument available to measure the interconnected pores. That's why mercury intrusion porosimetry is so popular. Okay, and also I would like to explain other methods. What are these principle? And what is the pore size it can measure also we can see. So MIP, as I mentioned earlier, it can measure 1 nanometer to 200 micron sizes. It is based on the principle of Ostwald equation, and also it is using a non-wetting liquid of mercury. Pore entry sizes can be measured. So I am going to talk about very detailed manner about MIP in the further slides. Okay. Next, the helium inflow technique. It can measure the pore size from 1 nanometer to 8 nanometer, and the flow of helium with the time is measured, and measure the microspace between the CHS layers. And a nuclear magnetic resonance, it can measure from 1.5 nanometer to 10 micron sizes. It works on the principle of interaction of nuclear magnetic moments with the externally applied electromagnetic waves in the radio frequency region. And a small angle X-ray scattering method. According to this method, the pore size can be measured from 1 nanometer to 100 nanometer. It is based on the principal measurement of intensity of X-ray scattered by particles. And if you come to the scanning electron microscope, it can able to measure 60 nanometer to 1 millimeter. The intensity of reflected electron is proportional to the atomic number of the substances in the object and the density of the material. That is the principle behind the SEM. Okay, so here you can get a clear idea about each and every instrument. What is the principle behind the instrument also you can see, and also the pore size ranges also mentioned. So among this, MIP is the only instrument can measure 1 nanometer 200 micron sizes, and also it can able to measure the interconnected pore. That is the biggest advantage. And another thing is it can able to measure the pore entry radius. None of the method can measure the pore entry radius except MIP. Okay, so now we can see what is wetting liquid, what is non-wetting liquid. Okay, so wetting liquid means actually the contact angle between the solid to the liquid, that is called a if it is less than 90, then it is called a wetting liquid. If suppose the contact angle between the solid to the wetted surface is more than 90, that is called a non-wetting liquid. So here you can see, so non-wetting liquid contact angle is more than 90 degree. So the mercury is one of the example for the non-wetting liquid, and water is the one example for the wetting liquid. Whenever we are putting a water on the surface, it will not remain as it is. It will used to flow. It is spreading on the surface because the contact angle is less than 90. Okay, that's why it is spreading on the surface. But if you drop a mercury on the surface, what will happen? It remains as like a ball. You can see there is the third picture. You can see the downside picture. So there is some mercury drops are there on the plank. So there are some cracks on the plank, but it is not going inside the cracks. It is remaining as a ball only. It's rolling on the plank only. This is called a non-wetting fluid because its contact angle is more than 90 degree. That is why it is falling in the category of non-wetting liquid. So now you can able to differentiate what is wetting liquid, what is non-wetting liquid. If your contact angle is less than 90 means it is wetting liquid. If your contact angle is more than 90 means non-wetting liquid. So mercury is a non-wetting liquid. That's why. So even though it is spread on the surface of the plank, it is not going inside the cracks and all. So unless until if you apply some external pressure or force, it will not go inside the cracks. It will remain as on the surface only. It is a remain its shape and it will remain on the surface only. Okay. It does not spread on the surface at all. Okay. Then I am coming to the MIP. So that's what I am going to discuss in this lecture also. MIP is called a mercury intrusion porosimetry. So what is the concept behind this MIP? The concept is very simple. We are just evacuating the sample and we are applying the mercury with a higher pressure. Depending on the voids or pores, the mercury will enter inside the sample. And there is a reduction in the mercury level. So that will be indicated by the attached porowind software. That's how we can determine what is the pore sizes of the particular sample and what is the porosity also we can determine. Actually here in the MIP there are 3 pressure stations are available. There are 2 low pressure stations and 1 high pressure station. In the low pressure station we are applying a pressure up to 50 psi. So there we are getting one cumulative intruder volume versus pressure curve. Then the same sample is transferred to the high pressure station, which is on the top side, that is the black one. So there we are keeping the sample and there we are applying the pressure from 20 to 60,000 psi. There also we are getting one more curve, cumulative intruder volume versus pressure curve. And finally we are merging both the curves together by using the software and we are getting the complete cumulative intruder volume versus pressure curve. So we can able to apply the pressure up to 60,000 psi. And also there is one mercury trap valve is there. In the right hand side there is one blue color you can see here. There is a mercury trap valve is there. The trap valve is kept in the liquid hydrogen. So the liquid hydrogen temperature is minus 150 degrees Celsius. So whenever you are handling this instrument, you should be very careful. If suppose the liquid nitrogen fall on your hand, means you will get the freeze burn. So generally we are familiar with fire burns only. It is a freeze burn because the temperature is minus 150 degrees Celsius. So we have to keep that, and also we should be very careful in handling the MIB because we are dealing with mercury. So mercury is injurious to health also. Even inhalation of mercury also sometimes problem. Even if the mercury is going inside your nails and whenever we are eating, if you are intake that mercury, it will also create some problem. Okay, so that's why we should be very careful while dealing this instrument. And this is very costly instrument also. Actually, this MIPs are generally produced by the USA only. So it is costing around 50 lakhs now. It is costing 50 lakhs. It is a very costly affair doing this experiment, but we will get a very good microscopic detail from this MIP. Okay. So this is actually in IIT Delhi Material Research Laboratory MIP. So actually, I have used this mercury intrusion porosimetry when I was pursuing my PhD at IIT Delhi. Okay. So these are the details of the instrument. So the name of the instrument is AutoScan Mercury Porosimetry. This is Kondravendhan. There are a number of manufacturers and brands are available. Among these, Kondravendhan is very popular. Okay, the model is called PoreMaster PM60. So the pressure range is up to 60,000 psi, from subambient to 60,000 psi. Otherwise, if you want to say in Pascal, it is 414 megapascal. The pressure accuracy is 0.25% of the full range. And the maximum intrusion is 2 cubic centimeter, and the volume resolution is 0.005 cc graphical, and pore diameter range is 400 to 0.035 micrometer. Okay, so as I mentioned earlier, mercury intrusion porosimetry is based on the Washburn equation. So what is the Washburn equation? Actually, as I mentioned earlier, mercury behaves as a non-wetting liquid because its contact angle is more than 90. It is having a 135 degree. That's why it is a non-wetting liquid, and it does not penetrate onto openings and cracks. Earlier slide also I have shown. Even though the mercury is spilling on the plank, which is having number of cracks, but it is not going inside the opening or cracks unless until if you apply some external pressure or force. Okay, so the pressure required is a function of the contact angle of the mercury. So and also its surface tension. These are the 2 parameters actually governing. That is nothing but Washburn equation, that is P equal to minus 2 sigma W cos beta by R. Here sigma W is the surface tension of the liquid and beta is the contact angle of the liquid and P is the pressure. Okay, so that's why the MIP is following the Washburn equation. Okay, so because here we are applying the pressure, that's how we are penetrating the mercury inside, injecting the mercury inside the sample. Okay, that's why it is following the Washburn equation. Okay, So here you can see actually in a mercury intrusion porosimetry, what we are doing, we are applying the mercury with high pressure. One time what we are doing, we are applying the intrusion and we are again doing the extrusion. We are taking back the mercury. Like that we are doing number of cycles. So that's why this kind of graph we are getting. So the curve 1 and curve 2 is showing. So first one is called the intrusion, then extrusion, again intrusion is happening. But you can see there is some mercury is trapped. Why it is happening? Because it is depending on the pore shapes. There are some inequality shape pores also there. Even though the mercury with the 60,000 psi can enter inside, but doing the extrusion, the whole mercury will not come out. That's why some mercury will be trapped inside the sample due to the inequality shape pores. Due to the shape of the inequality shape, we cannot take it out all the mercury. Some mercury will be trapped. So that's why we are getting the trapped mercury inside the sample. Okay. And so before starting this experiment, one has to determine what is the penetrometer constant. Okay, this is the penetrometer cell. Actually, it is a glass cell only, but it is very sensitive because it can able to bear the pressure up to 60,000 psi. But while handling this glass cell, you should be very careful because each cell costs around 20,000 rupees, and sometimes we are dealing with the hydraulic oil also. So it is a lot of chances it may spill, it may fall down from your hand. Then it is bit difficult for you. You have to procure again from the USA. It will take more time, 6-month period you have to wait. So that's why we have to handle it very carefully. Okay. So whenever we are going to use this penetrometer cell, first you have to determine what is the penetrometer constant. There are some procedures available. I am not going through the procedure. Just simply I will tell you. For where you are going to use the penetrometer, accordingly you have to calculate what is the penetrometer constant. So and again there are two type of cell is there. One is having the capacity of 2 cc. Another one is 0.5 cc volume. Okay, if you are using 2 cc, then what is the penetrometer constant in the low pressure station and what is the penetrometer constant in high pressure station? First you have to determine by using the standard procedure. Okay, that you have to determine. So I am skipping this procedure. Okay, just I will inform you. You have to determine the penetrometer constant. Then only you will get the accurate value. Okay. Then, as I mentioned, the mercury intrusion porosimetry is following the Washburn equation, and again Washburn equation is a function of contact angle and surface tension. So one has to determine what is the contact angle and surface tension. Before operating this instrument, we have to determine which contact angle you have to use or which surface tension we have to use. For that also, there are a number of people who have done a lot of research on this. So there are different trying techniques also used. Based on the trying technique only, we have to choose the contact angle and surface tension. For example, if you are using a oven drive, then we have to take contact angle is 170 degree and surface tension is 0.48 for Newton per meter. If suppose you are going for a pressure drive, then you have to use 130 degree and 0.48 for Newton meter. If suppose you are using a vacuum drive, then we have to take contact angle is 160 degree and 0.48 for Newton per meter. So there are a lot of literatures available. Based on the literature, you have to choose the value, and accordingly you have to insert in the software also. Okay. And this is the operating procedure. So this is also a very simple procedure, but it used to consume more time also. As I mentioned earlier, first you have to do the intrusion side. First you have to do the low pressure station. So first you have to clean the glass cell by using the isopropyl alcohol. So because it is very sensitive to dust also. That's why every time you have to clean the glass cell, and again you have to dry it in the oven. So once it is ready, then you have to keep your sample in the stem, and you have to cover it. So there are some procedure is there. So you have to cover it. Then you have to insert the sample inside the low pressure station. Then you have to do the intrusion extrusion cycle. So in the low pressure station, we have to apply pressure up to 50 psi maximum. Okay, so then we will get the cumulative interior volume versus pressure curve. Once you completed the low pressure station analysis, then you have to put it in the high pressure station. There actually we are not using the mercury. There we are using the hydraulic oil, high grade hydraulic oil. So there we are applying pressure up to 60,000 psi. There also you will get one more curve. That is also cumulative intruder volume versus pressure curve. That's how we have to do the operation. So generally it used to take around 1.5 hours for one sample, but for every mix at least we have to do 3 samples. Then we have to take the average. Okay, so this is the average cumulative intruder volume versus pressure curve. Okay, so this is done up to 60,000 psi, and actually we have to do 3 samples, and finally you have to take the average also. So taking average curve also not so easy. Further also you have to use some software. Okay, so that's how we got it. Okay, so now so far I explained how to use the mercury intrusion porosity, but now I can explain how one can perform actually. Okay, Actually, this concrete is a very complicated system. This is what I mentioned. So we can predict the compressive strength, permeability, everything through the pore structure parameters. So as I mentioned earlier, the pore structure parameters are R.5, D and P. P is the permeable porosity, R.5 is the mean distribution radius, and D is the dispersion coefficient. So this is a very complicated system, concrete. So if you see the micro level, still it is not so easy to determine. So this kind of research is very new, and we are pioneering this research also. So if you want to determine the pore structure, we cannot directly do this kind of work in concrete directly. So we have to take the simplest system. So simplest cement-based system is a cement paste only. So first you try to understand the cement paste, then we can gradually move to the cement mortar, then we can go to the concrete. So unless until you understand the cement paste, you cannot go to the concrete directly, because there are a lot of issues are there, like ITZ and all, we are not able to understand properly. That's why we have to start with the simplest system. That's why the first working has been started in the cement paste. Okay, so how to determine the pore size distribution parameters for the cement paste? For that, we have taken different water cement ratios, some low water cement ratios, some high water cement ratios, and some intermediate water cement ratios. For example, 0.2 and 0.3 are the low water cement ratios, 0.5 and 0.6 are the high water cement ratio, and 0.4 is the intermediate water cement ratio. And also we have taken two different types of cement. One is the coarser cement, another one is the finer cement. We can also determine the mean cement particle diameter by using the Angus-Smith particle size and shape analyzer. So we have determined the mean cement particle diameter by using the Angus-Smith particle size analyzer. So the coarser cement is having around 11.11 micron, and finer cement is having around 6.28 micron. That's how we determine the mean cement particle diameter. Otherwise, you can take it this way. One is a 43 grade OPC, another one is a 53 grade OPC, like that you can take. And we also tested for different ages also. One has to see how the pore structure is varying over the period of time. That's why we have taken the age also from 1 day, 3 day, 20 days, 56, 90, and 150 days, like that we have taken for the paste. Whereas in case of mortar, we have stopped curing age up to 90 days. Okay, that's how the initial test was carried out. So the sample is like that only. Actually, we have to take a small sample only. Whenever we want to test the sample in MIP, there are three possible things there. One is we have to cast the sample of small size. It is a pellets, like 9.5 mm diameter to 23 mm height circular specimen we have to cast. One is you have to cast the sample like this. Otherwise, what you can do, you can take a core from the big samples, like from a cube or a beam or whatever specimen sample we are having. From that, you can take a small bit of core, this size core you have to extract from the sample. Otherwise, you can crush the concrete from the crushed aggregate also, crushed cement paste aggregate samples you can take, and you can test it also. Those things will give erroneous result. This is the best way. You can cast the sample of size, because the size is limited. We cannot accommodate more than this size. Only we can accommodate 9.5 mm diameter to 23 mm height diameter only. So that's how the samples are cast of this size, and we have prepared for both OPC and OPC mortar also initially prepared. Okay, so whenever we are going to determine the pore structure of the cement-based materials, so the intention is to determine the pore sizes. First, we have to ensure the complete dispersion of the cement particles. So how to ensure the complete cement particle dispersion? We have to use the super plasticizer. If you are using the super plasticizer, we have to determine the optimum dosage also. How to determine the optimum dosage for the cement paste? For that, we have to use the Morse cone. So the Morse cone test we have to do. So this is not having any standard in India, but European standard is available. If you want to determine the optimum dosage for the cement paste, you have to use the Morse cone test. So here what we have to do, we have to prepare 1.2 liters of the cement paste. Then we have to pour it inside the Morse cone, and there is a 5 mm nozzle diameter is there. So through that, so we have to measure the time, how much time it is taking for 200 ml pass through the nozzle. So we have to start on your stopwatch, and you have to measure every 200 ml of paste pass through this 5 mm diameter nozzle. What is the time taken? That you have to measure it. So you have to start the dosages from lowest dosage, like let's say 0.25, 0.5, 0.75, like that. Gradually you can increase the dosage, and what is the time taken, you have to measure it. If you keep on increase the dosage, so the time will become quicker. Okay, at one stage, even though you are increasing dosage, there is no shortage of time will happen. So that means there is a optimum dosage. You reached it, then you have to stop it. That is your optimum dosage. That's how you have to determine the optimum dosage of the super plasticizer. Okay, so then for a flow table test, actually, you want to use for the cement mortar according to the IS 1727. So you want to do this. Okay, you want to prepare the cement mortar and you want to place it in 3 layer, and you want to give the 10 blows in 6 seconds. And what is the spread in diameter you want to measure? So from the spread in diameter only, 110 plus or minus 10, you have to get it. That's how we are getting the optimum dosage. Then we would determine for a different water cement ratios what is the optimum dosage of the superpolarization. Then you can plot a graph between optimal superpolarization versus water cement ratio for both the cements. Okay, then we want to go for the casting of the samples. So for that, we have used this kind of mold. So as I mentioned, this is the best way. Instead of going other methods, you can prepare the sample of required size. So you can, it is very easy to demold also. So, okay, once you prepare the cement base, you can pour it inside the hole and you can keep it for 24 hours. After 24 hours, you can simply remove the bolt net connection and you can remove the samples and you can keep it in the curing tank for the required age. Once a required age is attained, you can remove the samples from the curing tank and you cannot go for the testing immediately. Then what we have to do, we have to arrest the hydration. How to arrest the hydration? For example, I want to determine the pore structure for a 1 day age, 3 day age. So I cannot immediately do the MIP test. So that's why we are arresting the hydration. Even though you are taking out from the water, you are keeping outside also, the hydration will continue because there is inside some pore water is there. If pore water inside the concrete, it means there is a air drying will happen. So there is a hydration is a continuous process. It's an infinite process. So that's why we have to stop the hydration. How to do? There is a procedure. So you have to keep the samples inside the isopropyl alcohol in a beaker. Then the isopropyl alcohol beaker should be kept inside the desiccator. So the desiccator will maintain the relative humidity. So you have to keep this sample for 10 days. During the 10-day period, what will happen? The isopropyl alcohol enter inside the sample and it will replace the pore water. So now after 10 days, you can take it out the sample from the isopropyl alcohol and you have to keep the sample inside the oven for 105 degrees Celsius for 24 hours. Then you can take it out the sample. Now, so it become empty. So the pores are becoming empty. There is nothing is there inside. Now you can store the samples until you test the MIP test. Okay, you can store the samples. So here we are using the oven drying technology. Accordingly, we have to choose the beta and the gamma value. That is the surface tension and the contact angle value. So that's why we have to use 117 as the contact angle and surface tension is 0.484. That's what I told you. There are 3 different techniques are available for drying technique. So here we have used the oven drying. Some people use vacuum drying. Some people are using pressure drying. Okay, here we adopted the oven drying methods. So now the samples are ready. Okay, so actually if you look at the cross section of the penetrometer cell, it should be like this. So there is inside there is a cell, mercury can be filled there. That is a 2 cc volume and there is samples should be kept in the stem and you can see the mercury will be filled here and there is some electrical contact and cap will be there. Actually we are applying pressure like this way only. Okay, so this is actually a cross section of the penetrometer cell and every penetrometer cell is costing around 20,000 rupees. Everything you have to import from USA only, nothing available in India. Okay, so it is better to keep more samples because there are a lot of chances for getting breaking of this sample penetrometer cell also. Okay, this is the actual penetrometer cell. So and whatever the sample we cast and after hydration arrestation samples should be like this. So now you have to keep this sample inside the cell that is at the stem part. Then you have to put this cell inside the low pressure station. Then we have to apply the pressure up to 50 psi by using the attached Corovin software. So once the low pressure is over, then we have to switch out the high pressure station. The high pressure cavity should be like this. So here we are using the hydraulic oil. Okay, so there we have to apply pressure up to 60,000 psi. So then we are getting at least we have to do 3 samples. We have to use 3 different samples we have to do for the same mix. So then we have to take the average. So we are taking the average curve. So now it is on 3 experimental data and there is one average curve also done. All are in cumulative internal volume versus pressure curve. That's how we have to perform the mercury induction porosity test. So here it is better explained how the mercury is penetrating inside. Actually you can see first we are creating the vacuum, then we are applying external pressure that is 60,000 psi is giving. That time the mercury is entering inside the vacuum is removed and it is entering inside. That's how the mercury is going inside the voids. That's how we are measuring the porosity and pore sizes. Actually the ATAL software will give you directly the porosity and pore sizes. Okay, so this is how it is for forming. So next, how to calculate the average curve. So actually it is not so easy because we are getting three different cumulative integral volume versus pressure curve. Then we have to see how to take the average. For that we used a Morgan-Mercer floating model. Actually this kind of model mostly biological science people are using. Actually it is a freely available curve expert software. Actually we used it. It's a open source. Anybody can use the software. From this curve we came to it is a S-shaped curve and it is having this kind of equation. So even if the curve is passing through the origin, then automatically the intercept A will become 0. Then the curve will become like this. The second equation, that is V equal to Cp power D divided by P plus P power. That is called a Hill equation. Then again using the Wassermann equation, we can replace P equal to P 0.5 power D. Then automatically we will get the equation. What I was telling at the beginning, the force distribution is governed by 3 parameters. That equation I got it. So now I can say the force distribution is governed by 3 parameters. That is, one is permeable porosity P, R.5 mean distribution ratio, and the dispersion coefficient D. So these 3 parameters you can easily calculate by using your experimental data. So experimental work anybody can do. If you know the procedure, we can determine force distribution parameters, and you can calculate also. Only just you have to understand how to perform the experiment. Okay, there is not much complication, but only thing is it's a DDS process, and we have to do all the procedures, and we have to do hydration registration, all the procedure we have to follow strictly. Okay, then if you plot this is the experimental data. So if you plot a R.5 versus curing age, how it looks like for a typical water cement ratio, it is shown. The R.5 actually it is reduces over the age. So why it is happening? Because due to the progress of hydration over the period of time, there is a refinement is happening. More and more CH gel is forming. That's why the pore size is reduces, and after some time, what will happen? It is becoming asymptotic to x-axis. That's how the R.5 versus age curve will behave. If you plot a dispersion coefficient versus age, you will get this kind of curve. What is happening here? The D is increases over the age, because here also what is happening due to the progression of hydration, more and more CH gel is forming. That's why the distance between the R.5 is increasing. That's how D is keep on increasing over the period of time. So again, it is also becoming asymptotic after some time. Okay, so D will behave with respect to age like this way. Okay, so these are all the experimentally determined data, and we can also determine the experimental porosity value also. So there is no big issue, but this is very simple. But is it possible to model the pore size distribution parameters? So theoretical models. So that will be challenging, because doing experimental work anybody can do. Even I can train a labor, he can do. I can tell you to operate this like that. If you are telling, he can do. But actually, our engineering skill should be reflected in the theoretical model only. So how we can do the theoretical model for the R.5 D with respect to water cement ratio and age? Okay, if you see the cement particle, how the hydration will take place. Generally, if you consider a single cement particle, so once it is added with water, how the hydration is taking place, it will form two kind of products. One is called a inner product, another one is called the outer product. You can see here the right hand side figure, I am showing different colors. One is inner product, another one is outer product. Actual diameter of the cement is D. So after the formation of the inner product, the diameter is becoming DA. So after formation of the outer diameter, the diameter is become D0. So now we can able to differentiate. The original diameter of the cement particle is D. After the formation of the inner product and outer product, the diameters are different, and accordingly I put it different names also. So DA is the inner diameter, and D0 is the outer, including the outer product. Okay, so that's what we have to mention now. So for a complete dispersed cement particle system, we can also determine the mean distribution radius. How to determine? For that, we have taken single cement particle surrounded by a water in a cube is considered. This kind of approach we have done it. Only for a completely dispersed system, we have taken single cement particle surrounded by a water in a cube. So that's what we consider. So we have calculated. We can able to calculate what is the volume of the cube. That is nothing but cubic root of volume of the cement plus volume of water. That's how we have calculated here. Gamma, sigma, rho C and rho W are the density of cement and density of water. And again, you can see hydration, the physical changes. What is actually happening physically? What will happen? You can see initially the cement particle is a irregular shape, right? Am I right? It should not be circular. But for design purpose, I cannot keep it as irregular. So I am converting it to regular shape. It's a circular shape. I am assuming a circular. Now there is an inner product is forming. Okay, this is what happening actually in the hydration process. There is an inner product CH gel is forming, then outer product is forming, Then there is a unhydrated cement particle is there. Then there is a calcium hydroxide at Portland ice is forming, and remaining there is a capillary porosity is forming. That's what actually physically how the hydration will take place. This kind of thing you cannot find anywhere. Okay, so in a single cement particle, how it is reacting. So that's what I explained here. So initially inner product is forming, then outer product, then there is an unhydrated cement is there, then calcium hydroxide formation and capillary pores. These are all things are happening. Okay. Then next, you can also determine what is degree of hydration. Degree of hydration is nothing but mass of the cement reacted to the total mass of the cement. It's a ratio between the mass of the cement reacted to the total mass of cement taken. So that is called the degree of hydration. That's how we can determine the degree of hydration. Then we can also calculate what is the mass of water reacted within the unit cell. Okay, and also we can calculate what is the total mass of the hydrated product. That is nothing but the summation of the mass of the cement reacted plus mass of the water reacted. Then also we can calculate what is the volume of the solid product including the inherent gel pores. We have calculated accordingly, and that is nothing but the difference between the inner product and the outer product. That's how we calculated a capillary entry radius is nothing but L minus D naught by 2. So after simplifying this, we came to know capillary entry radius as a function of water cement ratio and alpha. Alpha is nothing but degree of hydration. Here K1, K3 and all nothing but it's a safe factor. If suppose you are assuming a circular, it will become pi by 6. Then again, how to determine the degree of hydration? So for determining the degree of hydration, actually we have referred the literature. And in literature, actually there is no standard relation is available. There is no standard relation is available. What I want to know, we want to have a degree of hydration as a function of water cement ratio and curing ages, but there is no such relationship available in the entire literature. So, but fortunately we came to know there are 3 relationships available, but that also having some problems. Let me discuss what is this. So first we got a Lambertal degree of hydration. Actually he has given degree of hydration as a exponential function of the exponential function. There are some parameter A and B also there. Again, it is a function of only water cement ratio. But actually, degree of hydration is governed by water cement ratio and curing age. But here, whatever the Lambertal has given, it is a function of only water cement ratio. So it is having a restrictive. So we cannot use it. So then again, we have seen there is one more Avrami degree of hydration is available. Again, here also the degree of hydration is as a function of only curing ages, and also he has given only for 7, 28 and 90 days only. Again, it is not a function of water cement ratio. It is also ruled out. It is not solving our purpose. Then we have seen there is a case pan et al. Degree of hydration. He has given degree of hydration versus water cement ratio for different curing ages. So, but he has given a plot. But it is somehow it is matching with our intention. So we have taken this case pan et al. Degree of hydration and we have extrapolated the data and we have done some multiple regression analysis. That's how we got this previous equation. Degree of hydration as a function of water cement ratio and curing ages. Then actually this difficulty actually it instigated us. Why not we determine the degree of hydration? So no such relation is available in the literature. Like that, it is stimulated us. Then we thought we will determine the degree of hydration as a function of water cement ratio and curing ages. Then we started some experiment on this direction. So what we did, so we started determining the non-evaporable water content. Actually, the mixed water, whatever water we are using for mixing the mix, for example, concrete or cement paste, whatever mix you are preparing, the mixed water consists of 2 types of water. One is evaporable water, another one is non-evaporable water. So evaporable water one can determine by heating the sample to 100 degrees Celsius. But how to determine the non-evaporable water? If you can able to determine the non-evaporable water, it is also possible to determine the degree of hydration. Because according to the TC power, so 1 gram of cement is having 0.23 gram of combined water or chemically bound water. This is already done. It is already available in literature. In 1960, he has revealed this matter and he has done around 30 pages of experiment and he came to know 1 gram of water is having 0.23 gram of combined water. So by using that concept, we can also able to determine what is the non-evaporable water content. So we have done the experiment on the cement paste for both the coarser and a finer cement. We have done the experiment and we have determined according to TC power. So non-evaporable water content can be determined using the formula, that is W1 minus W2 by W2 minus LOI. Here W1 is the dried weight of the cement paste at 100 plus or minus 5 degree. That is called evaporable water content. So W2 is the ignited weight of the paste 1000 plus or minus 50 degrees Celsius for 3 hours, and LOI is the loss on ignition. So if you can determine by using the muffled furnace, you can determine this non-evaporable water content. So we have determined for number of samples for different water cement ratios and different curing ages also we have determined, experimentally we have determined. So once you know the non-evaporable water, we can also able to calculate what is the degree of hydration. Degree of hydration is nothing but non-evaporable water divided by 0.23, because 1 gram of cement is having 0.23 grams of combined water. That's how we can determine degree of hydration is WN divided by 0.23. So we will determine the degree of hydration for various water cement ratio and various curing ages, and also we have plotted for cement 1 and cement 2. Those figures are looks like this, and obviously cement 1 is the coarser cement and cement 2 is the finer cement. So cement 2 is having more degree of hydration and cement 1 is having less degree of hydration, and over the period of time it is increasing also. It is increasing rate because more and more CHG gel is forming. Okay, so this is then again by using this data we also done some least square based regression analysis, and we got a degree of hydration as a function of water cement ratio and curing ages. Now this kind of equation is available. So now we have found a degree of hydration as a function of water cement ratio and curing ages. So by using this equation in the capillary entry radius, now we got the capillary entry radius as a function of water cement ratio and curing ages and mean cement particle radius. So now one can able to determine what is the mean distribution radius or R.5 for the capillary entry radius. We can determine by using these 3 parameters. Only you go to give the input, what is the water cement ratio, what is your curing age, at what age you want, and what is your mean cement particle time. If you provide these 3 parameters, you can calculate what is the capillary entry radius. Actually, beyond the curing age of over the period of time, what is happening? The capillary pores are getting segmented because the hydration is a continuous process. Over the period of time, the capillaries are becoming segmented. So it is blocked by the gels. More and more CHG gels are forming. Then there is a interconnectivity is affected or blocked. That is called a segmentation. So one can also calculate what is the segmentation age of the pores. Okay. So by equating the capillary entry radius equal to 0, you can calculate what is the segmentation age for different water cement ratios. So we have estimated the segmentation age for 0.3, 0.4, 0.5 and 0.6, and also we compared what is the value available in the reported literature. If you look at your Neville and Brooks book, this is given, the reported values. For 0.4 water cement ratio, it's 3 days. 0.5 it is 14 days. 0.6 it is 180 days. But our estimated values also closely matches with the value. That's why we can cross check it. We are going in the right track. So our research is going on the right track. That's how we ensure it. Because our values also nearly matches with the reported values. Okay. So then we also calculated beyond the curing age of capillary segmentation, the pores are gel pores. Before that, we calculated the percolation threshold also, because it is very relevant to calculate what is the permeability kind of things. So the percolation threshold also we can calculate by using the segmentation age. By using the segmentation age, we also calculated the percolation threshold for different water cement ratio. Okay, and beyond that, before that, this models also available. What is the porosity models for the cement base? This is ready-madely available. You can see in Neville and Brooks book. You can get the gel porosity formula, capillary porosity, and total porosity. So gel porosity is 0.19 H. H means degree of hydration. I used alpha. They used H. Okay, H and alpha both are same only. Divided by W by C plus 0.317. Capillary porosity is W by C minus 0.36 alpha or H divided by W by C plus 0.3. These are already established and it is available in the ready-madely available. So you can directly take the powers model porosity is available. You can take it. Okay. But beyond the capillary segmentation, the pores are gel pores. If you look at a particular water cement ratio, it is having a function R.5 gel is A by T and P, and A and P are raised to the power of water cement ratio 4. It is fitting best. That's how we got the R.5 gel having this kind of relation. Okay. Now finally, you can calculate what is the overall R.5. Overall R.5 is nothing but the weighted geometric mean of R.5 gel into P gel into R.5 cap into P cap, or otherwise I can say Ln R.5 equal to. So that is another form I have written. Here P gel is nothing but it's a fraction of gel porosity to the total porosity, and P cap is nothing but the ratio between the capillary porosity to total porosity. That's how we got the relation for the R.5. Now one can able to calculate the mean distribution radius or R.5 by using 3 parameters. Yeah, anything? Any doubt? Hello? Can I go ahead?
Yes, sir. Kindly go ahead. There's nothing.
Okay. So that's how we can calculate what is the R.5. We can calculate. It is a function of water cement ratio, curing ages, and mean cement particle. Next, we will determine the model for the dispersion coefficient. Again, if you look at the dispersion coefficient, it is increases with respect to ages. Okay, because more and more CHG gel is forming, and again it's a function of the degree of hydration. That's how we got a dispersion coefficient as a function of water solubility ratio and curing edges. So we got a model for dispersion coefficient also, R.5 also, already permeable porosity P also available. Now we can able to you are having the relation for all the three parameters R.5, D and P. Okay. Now what is the point? Why we would determine all the things? Is there any application? That's what I am going to discuss next. So okay, when we have compared this also, what is our estimated and experimental and percentage error also calculated. Okay, those things you can refer here. Okay, so D values also. Now I am talking about the implication or application. Why we want to determine? It is also possible to determine the compressive strength. Generally, if you look at the literature, mostly they have given compressive strength is governed by the porosity only. Actually, that is not correct. Actually, the compressive strength is not only governed by porosity, it is also governed by pore sizes also. Only very few people have done this kind of work. Actually, very beginning, actually ATAL has done such a work. So he incorporated the pore sizes along with the porosity. Then later on, Kumar and Bhagath also given such a relationship that is sigma equal to Kc into 1 minus P divided by R.5. Then for cement paste, we slightly modified that. Because in cement paste, we have to consider the degree of hydration also. That's how we got a sigma equal to Kc alpha into 1 minus P divided by R.5. Here K is the proportionality constant that actually governs the modulus of elasticity of the cement matrix and also the surface area, and C is the cement content in the concrete mix, and alpha is the degree of hydration. So determine the K value, the constant of proportionality. We have taken around 200 experimental data from the literature, and we plotted the experimental compressive strength data versus C alpha into 1 minus P divided by square root of R.5. From this we got a K equal to 1002.6. So okay, so now we can able to predict the compressive strength. Okay, then again we have to check it, because we know the Abraham's law. Abraham's law is nothing but strength is inversely proportional to water cement ratio. So now we can also estimate the compressive strength for different water cement ratio and different curing edges by using a relation, and we can plot the estimated compressive strength with the water cement ratio. That is also behaving in the same manner. But if you look at the picture, so the graph, the 1 day, 3 day, and 7 days, the pictures are not very smooth. The graph is not smooth. Why it is happening? Because the segmentation is happening at the early edges. In case of 1 day, 3 day, and 7 days, the segmentation is happening early. That's why the pores are only gel pores. That's why it is showing the somewhat not smooth curve. Okay. Otherwise, it is showing the same curve. That's how we can prove our estimated or whatever prediction formula we revealed is matching with the existing theory. Okay. Then we also extended this work to permeability. So earlier, the Pradhan and et al. Have done some work on hydraulic conductivity and permeability. Actually, hydraulic conductivity and permeability both are same only. If suppose in the unsaturated condition we call it as hydraulic conductivity, in the saturated condition the theta will become K. So that's how we can say hydraulic conductivity and permeability both are same only. So he has given the relationship for the permeability. According to this relation, actually he kept the porosity as a linear function with the permeability, but actually that is not true. Because over the period of hydration, there is some segmentation is happening. That's why, according to the Reinhardt and Weber, the porosity should be raised to a certain power of m. That m is nothing but interconnectivity factor. So one has to modify this relation. That's how we modify the relation. So we have to determine the m factor. That is called the interconnectivity factor. For that, we have done some innovative procedure. We have taken a number of literature available permeability value and what is the corresponding water sedimentation curing edges. We have calculated through our estimated permeability, and we have taken the ratio between our experimental value and our estimated value. That is called the K ratio, and we have taken m value randomly, like 0.5, 1, 1.5, like the number of values we have taken. Then we have plotted a graph between K ratio versus m, and from the curve we got what is the actual m value. So we got the interconnectivity factor for the cement basis m equal to 2.67. So now by using this, we can also modify the permeability formula. Then we can plot the graph permeability versus water cement ratio. We can get this kind of curve. So this kind of curve also in 1962. So that TC Power has given. After that, nobody has done this kind of research. Now we can ensure. So whatever the prediction formula we have given is correct, because it is also following the same trend only. Okay, that's so we happy with this outcome. And again, we have done validation also. So for that, we have taken the integrated absolute error index. So by using this formula, we can also calculate what is the percentage of IA index. So OI is the observed permeability and P is the predicted permeability value. So by using this formula, we can calculate and IE index is coming 8.62. If it is less than 10 means it is correct. So it is valid. So that's how we validated our work also. The next we have gone for the hydraulic diffusivity. Hydraulic diffusivity is nothing but hydraulic conductivity to the specific water capacity. So then we can also modify K theta into D psi by D theta. That is called suction head. These formulas are already available in literature. Only just to be taken the K theta, that what we have modified. By using this, we have calculated the hydraulic diffusivity for both the wetting and drying cases. So hydraulic diffusivity one has to determine wetting and drying cases. In case of wetting, what is happening? The larger pores are filled first, followed by the smaller size pore. That's how the least water cement ratio is the largest pores. Whereas in case of drying, it is starting from the largest pores drying, then gradually it is coming in the lowest pore. That's how the least water cement ratio is related to the smallest pores. If you plot the hydraulic diffusivity versus relative moisture content, you will get this kind of curve. Again, it is matching with the Hall-ATAL equations. So same kind of equation also produced by the Hall-ATAL for the hydraulic diffusivity. That's how we can say the work what we carried out, what our prediction formula given by us is matching with the existing literatures, and this is the right direction. Okay. So then we have extended this work for the cement sand mortar also. But here the one complication is there, because once we introduce the sand particle, so that is due to the wall effect and loosening effect of the particle, it is inducing some ITZ porosity. Actually, there is no idea available so far how to quantify the ITZ porosity. Even Power's model is not incorporating the ITZ porosity. That's why it is not possible to do the theoretical modeling. So that's why we have done only empirical modeling only we have done it. So, but then again we have seen the application also. We have done the similar kind of exercise for the compressive strength prediction and permeability prediction. Everything we have done the same way, and also hydraulic diffusivity. All are falling in the same nature. Okay. So now we also did the integral absolute error index, and here this IA index is coming 0.04. That means it is better. Okay. So up to 10% is okay. Okay. So from this, what I want to conclude, so it is possible to determine the pore size distribution parameters by using the water cement ratio, curing age, and mean cement particle diameter. Once you know the R.5, D, and P, it is also possible to determine the compressive strength, permeability, and hydraulic diffusivity. And also, once you know the water cement ratio and curing ages and mean cement particle diameter, if you can able to predict the degree of vibration. So all these things are we have derived through our exercise. Okay, that's what I mentioned in the conclusion. So now I am actually coming to our cement fly ash system, because we cannot directly come to the cement fly ash system. First we have to start with the simplest thing. So that's why I started with only OPC paste. Now I am coming to the cement fly ash system. So here actually we use different water cement ratios. That is water by binder ratio. That is 0.25, 0.35, 0.45, and 0.55. So we use the cement fly ash, and curing age is varied 7, 28, and 90 days. And we have to replace the cement with 4 different percentages. So on control, 10, 20, 30, and 40. That is F by C ratio, I can say. So that's how we started this cement fly ash system. So here also we have done number of tests on the cement fly ash paste and cement fly ash mortar. So we also determine compressive strength also. Okay, so as I mentioned earlier, first we have determined what is the optimum dosage, because our intention is to determine the post size distribution. So we have to ensure the complete dispersion of the cement particle. Otherwise, we cannot get the complete hydration also, because the hydration, it needs some space also, space between the particles. Whenever you are using superposition, it is giving a negative zeta potential. That's how the cement particles are getting dispersed properly, and there is a space available for the inner product and also outer product, that we can achieve by using the superposition. So we will determine the optimum dosage of the superposition for the cement fly ash paste and also cement fly ash mortar by using the mass cone test and this flow table test. Okay. Then yeah, these are the optimum dosage. Then we have determined the compressive strength. The compressive strength is increases even beyond the 28 days because of the secondary pozzolanic reaction. Actually, the fly ash we have used from the Dadri power plant, which is around 50 km away from the Delhi in Uttar Pradesh. So from there we got the class F fly ash we have used here. Okay, that's how we got the compressive strength like this. Then again, how to determine the degree of hydration for the cement fly ash phase. In case of OPC, it is very simple, because BRTC power already developed something. There is a combined water for the cement. We know 1 gram of cement is having 0.23 gram of combined water. That's why we can determine it quickly without any hesitation. But in case of cement fly ash, we are adding one more material, that is fly ash. Then how to determine the degree of hydration? So then we have referred some literature. Actually, there is one person, Northern Squares and Naitala has conducted work on this degree of hydration. From this, we came to know the degree of hydration. The total degree of hydration for the cement fly ash system is nothing but summation of the degree of hydration of the cement and the mass fraction of the cement plus degree of hydration of the fly ash and the mass fraction of the fly ash. That's how we have calculated that. We have done a lot of experimental work, and we have determined degree of hydration for various water cement ratios and curing ages, and finally we have done the least square based regression analysis. Finally, we got a total degree of hydration for the cement fly ash paste is a function of curing age and a water cement ratio. Otherwise, I can say W by C plus F and also F by C ratio. So if you know these three parameters, you can also be able to determine what is the degree of hydration for the cement fly ash system. So we have determined the degree of hydration as a function of water binder ratio, F by ratio, and ages. Okay, and again, how to determine the porosity? Because in case of OPC paste, mortar and all, the standard formula is available. If you refer the Neville and Brooks book, it is available. So what is the gel porosity? What is the capillary porosity? What is the total porosity? Everything is available on the literature. But in case of cement fly ash system, nobody has developed. But by using the theory, we can also develop. So okay, that's how we attempted here. So if you look at cement fly ash system, so what is the volume proportion? We are using cement and fly ash and water. This is our original volumes. Okay, so VC is the volume of cement, VF is the volume of fly ash, and VW is the volume of water. If you mix together all the things, then what will happen? So what are the end product you will get? You will get a hydration of the cement, hydration of the fly ash, and some unhydrated cement, unhydrated fly ash will be there. So if you know the initial volume, and if you detect this hydrated product and unhydrated product, the cement and fly ash, the remaining thing is nothing but capillary porosity. So one can also able to calculate the capillary porosity. That's how we calculated the capillary porosity. First we calculated what is the hydrated cement product. We also calculated the hydrated fly ash product, and what is the unhydrated cement and what is the unhydrated fly ash also we calculated. Then initial volume minus this, we calculated the capillary porosity. And the capillary porosity divided by the original volume or initial volume will give you the capillary porosity. Okay, so total volume. Okay, so total initial volume we know. So what is the capillary porosity? We can easily calculate, because porosity is volume of voids to the total volume. That's how we calculate the capillary porosity. So it is also possible to calculate what is the gel porosity also. That also we have calculated. And we can also calculate what is the total porosity. The total porosity is nothing but summation of the capillary porosity and total gel porosity. Okay, that's how we calculated the total porosity also. So we have calculated the porosity by using this volume proportion, and we calculated. Then how to do the modeling of the R.5 in case of cement fly ash system. So because the packing of cement and fly ash is not known to us, so it is nowhere it is available, then it is not so easy to do the modeling. Then what we have done, so we consider hydrated products of cement fly ash and unhydrated products of cement and fly ash are stacked together and is making us a sphere inside the cube. That's what we assume, and we calculated the equivalent diameter. Actually here we are using the equivalent diameter of the sphere. That's how we calculated the R.5 capillary entry radius. So equivalent diameter concept we used here, and we calculated R.5 capillary entry radius is nothing but the volume of the cube, that is L minus T equivalent divided by 2. By using this, we calculated what is the equivalent diameter of the hydrated and unhydrated product, and L is the length of the cube. By using this, we calculated what is the capillary entry radius. Then again, beyond the curing age of capillary segmentation, the pores are gel, as I mentioned earlier. So again, we have to determine what is the gel entry radius. So here again, initially tried with the water cementitious ratio like W by C plus F, but that is not fitting well. That's why we modified, and we came to know volume of water to the volume of binder is fitting well. So that's why instead of water by binder ratio, we use the volume of water to the volume binder ratio. That's how we got this kind of relation for the R.5 gel entry radius. So finally, we got the overall R.5, the same formula what I proposed in case of OPC paste. Similar kind of relation we got for the cement fly ash paste also. That is R.5 is the weighted geometric mean of R.5 gel into P gel into R.5 cap into P cap. Okay, so you can take the LNR in both the sides. The second equation you will get it. Here P cap and P gel are the fraction of the capillary gel porosity to the total porosity. So then similar manner, what I established in case of OPC paste and OPC mortar, we have done the dispersal coefficient model also. So here dispersal coefficient is a function of water binder ratio and curing edges. Okay, so we also established the relationship for the dispersion coefficient. And what is the application? So now we have to look for the application, because once you have modeled the process distribution parameter, then what is the implication or application? So here already we established the relation between the process distribution parameter with the strength in case of OPC base. Here we slightly modified. Instead of only using the C, we are adding the F also. That's how here the formula is becoming sigma equal to K into C plus F. Okay, instead of C, I am using C plus F. Remaining things are same only as like previous one. Okay, so then again to determine the constant of proportionality K, we have taken the number of experimental data and we have plotted the experimental compressive strength data versus C plus F into alpha into 1 minus P divided by square root of R.5. That's how we got the K value also. Then by using this value, we can also able to predict the compressive strength of the cement fly ash paste. Then we also checked the Abraham's law. Abraham's law, what it says, strength is inversely proportional to water cement ratio. So we are getting the same trend for different water bend ratio and different curing edges and different F by C ratio. We have done it for all these exercise and we got the similar trend. Now this is also correct. Like that we can ensure. Okay. So this kind of work has been carried out in case of cement fly ash phase, and also we have determined the permeability also. Then again we plotted the permeability versus water bend ratio. This is also following the same trend as mentioned by the TC power ATAL. So we are getting the similar kind of trend, and we also determined the hydraulic diffusivity for both wetting and drying cycles. So this is also following the same trend as mentioned by Hall et al. For the hydraulic diffusivity. We have determined both wetting and drying cases, all are following the same category. Then we have gone for the cement fly ash mortar. So here also again the problem is there, because once we introduce the sand, so because there is no IDZ porosity quantification is available in the literature, and again doing this is a very voluminous work, because we have to change the paste content and we have to use a different volume proportion of the aggregate. Like that we have to do separate research on, then only it is possible. But initially we have taken only one paste content only. We have to take more paste content as compared to the void ratio. That kind of exercise we have not done it. That's why it is not possible to do the modeling in case of the cement fly ash model also. Then we have done the empirical modeling only. So here also we got the R.5 as a function of water binder ratios and F by C ratio, and D also we got the function of the water binder ratio and the F by C ratio. Then we have done the same kind of exercise, like we have determined the compressive strength versus C plus F into alpha into 1 minus P divided by square root of R.5. We calculated what is the constant of proportionality K, that is 1559.2. So by using this, we can also able to estimate the compressive strength for different water cement tissues and different curing edges, and we can also check the Abraham's law also, one can check. Okay, and we put all the data together, and we got one common relationship for the cement based material. So that case we got a K also 1081.6. So that kind of exercise we have done, and we also extended this work to the permeability and hydraulic diffusivity also. So in the case of permeability also we got the similar trend. So the permeability versus water binder ratio we got it. So that is also showing the same trend that predicted by the TC power in the year of 1960 for a different water binder ratios and EH you can see. So and this work has been extended to the hydraulic diffusivity, and there also we have done it for both wetting and drying cycles, and the hydraulic diffusivity versus relative moisture content has been given in the graph. So here also if you look at the equation, it is also matches with the equation what is given by the Hall et al. For the hydraulic diffusivity. Okay, then from this what I want to conclude, so it is possible in case of cement fly ash system also we can predict the process distribution parameters like R.5, dispersal coefficient D, and permeable porosity P. Okay, we have developed a model for the porosity because it is not available in literature. In R.5 also we developed, dispersal coefficient also we developed. Okay, so but all the parameters are as a function of simple mixed factors only, that is water cement ratio, curing age, and mean cement particle diameter. Here we are using F by C ratio. Okay, so by using this we can able to predict the process distribution parameter. Once you know the process distribution parameter, it is also possible to predict the compressive strength, permeability, and hydraulic diffusivity. So this is possible. Okay, so these are all the works carried out for the cement fly ash paste and mortar. Now I am coming to my last part of my presentation, that is for concrete. So because so far I have talked the simplest system like the paste and mortar, it's also possible to do in concrete. For that, what we have done, this work actually carried out by one of my friend in IIT Bombay. His name is Dr. B.B. Das. Now he's working in NIT Surat. Actually, he has carried out this work actually. So what he did, he used crushed concrete chunks for the different grade of concretes. So he used the PPC cement, and he has done I think three grade of concrete he has done it, and he tested the concrete samples for 1, 3, 7, 28, 56, 90 days, and he has determined the postage distribution parameters, and he using the postage parameters he also calculated what is the compression, permeability and hydraulic diffusivity, that he has done it. Okay, so that's what I am going to present. Here you can see, here he has not cast the sample, because in concrete, because the size is very small, so we have to take a core, but instead of taking a core, he has used the crushed chunk of the aggregate with cement matrix. That's what he used here. Okay, so he calculated this kind of curve, he got it for a M30, M40 grade also he have done it. So accumulated interior volume versus pressure curve. This is only experimental work he has done it. Okay, then he has plotted the mean distribution radius versus age. So for a M20 grade, M30 grade and M40 grade he has done it. Okay, then dispersion coefficient also he calculated for all the three grades. Okay, so he has plotted the dispersion coefficient versus age. This is also showing the same trend, because the dispersion coefficient increases over the period of time due to the substantial degree of hydration or the progression of degree of hydration. It will happen like this. Okay, and again he determined what is the constant of proportionality. So once we determine the postage distribution parameter, we go to determine what is the relation, what is the application, how we can determine the composition. As I mentioned earlier, sigma equal to Kc into 1 minus p divided by square root of r.5. Here we should not use alpha. Alpha is applicable only in case of paste and mortar only. Okay, so directly you can determine K value by using your compression data versus C into 1 minus p divided by square root of r.5. That's how we calculated. So this K value is coming 100,796.1. Then he also extended to the permeability and hydraulic diffusivity also. He plotted the hydraulic diffusivity versus relative moisture content for both wetting and drying cases. So he has plotted. So this guy, actually he has done only experimental work only, but he has extended to determine the, by using the experimental postage distribution parameters, he calculated what is the compressive strength, permeability and hydraulic diffusivity. He has not done any modeling. Actually there is a scope, so one can do modeling for the concrete postage distribution parameter also. So maybe in future I am planning to extend this work for concrete also. Okay, so whatever I presented here all are published. Okay, so all are published in the world reputed journals like AC Materials. This is the #1 journal for civil engineering is concerned. Okay, you can see all the leading journals like Magazine of Concrete Research, and again one more AC Materials journal. Okay, materials characterization, so construction building materials. Okay, so you can all the details are available in the literature. All are published in leading journals. Whatever data I presented here, all are available in the literature. So you can refer those literatures and you can get all the details. If you want further details, you can refer the thing. There are few conferences also we published. These are some of the references we have done it. I think this kind of work one can extend for a different kind of concrete also, because this is only the level of starting stage only. So this has been recognized by the international scientific community. So it is possible to predict the compressive strength of the concrete by using the microstructure parameters or core structure parameters. So that's what I want to conclude from this literature. Okay, so with this I am stopping my lecture. If you have any doubt, we can discuss now. Okay, this is open for discussion now.
Yes, very comprehensive presentation by Dr. Vendhan.
Yes.
Until now, we have been thinking, understanding that microstructure studies can only be qualitative, but you have proved that it can be lead to quantitative determination as well.
Yeah.
So it will definitely pave the way for further research and further work in this area. Participants may please ask any question.
Yeah, I'm happy to discuss with you. If you have any doubts, you can raise your doubts, please.
Of course, feedback is very. Many participants has given me on Google Form link also the excellent presentation, and that's all. But participants are invited to ask questions, if any. If there are no questions, can we thank the learned speaker